Hello there, and welcome to Science for Sleep, where curiosity drifts gently into the night and science becomes a soft companion rather than a lecture. Tonight we'll explore something that at first glance sounds like the simplest idea in the world, and yet is one of the strangest concepts science has ever tried to understand. It is the idea of emptiness. Not the everyday kind you feel when your cupboard is out of snacks, or when you notice the last slice of cake has mysteriously vanished. No, we're going to step into the scientific idea of nothing itself, the vacuum, the space that appears to be bare and hollow, and then realise that this so-called nothing might actually be everything. Think for a moment about the air around you. You breathe it in, and it fills your lungs with oxygen. You breathe it out, and carbon dioxide leaves your body. Even when you can't see it, you know the air is there. Now imagine you had the power to remove that air completely, to take away every last molecule of oxygen, nitrogen, water vapour, dust and tiny pollen grain. You're left with an empty jar, aren't you? Or at least that's what it feels like. But physicists would gently tap you on the shoulder and say, "Not so fast. That emptiness is not so empty after all." Before we dive too deeply into this curious world, let me ask you a simple question. Where are you listening from tonight? Is it a quiet bedroom with the light low and the covers tucked close? Or are you stretched out on the couch with the day finally behind you, letting words float in while your eyes grow heavy? And what does the night sound like where you are? Maybe the hum of a fan, the soft patter of rain, or perhaps just the hush of stillness. Wherever you are, this moment is yours, and together we'll wander through one of science's most fascinating puzzles. If you find this little voyage calming, or if it helps you unwind after a long day, I'd be grateful if you pressed like or subscribed. It helps this quiet space reach others who may need the same comfort, a chance to slow down and let curiosity ease them into rest. But for now, just let yourself sink into the rhythm of this voice, because we're going to travel into the vacuum, into the strange truth of nothingness, and see how in physics, nothing is never truly nothing. When people long ago thought about empty space, they often imagined a pure void, a place stripped of all matter. Philosophers in ancient Greece, for example, debated endlessly about whether a true vacuum could even exist. Some argued that nature abhorred it, that emptiness was impossible, that the universe always rushed to fill gaps the way water pours into cracks. Others said no, there must be nothingness somewhere, an absolute void. They pictured it as a silent backdrop to everything else, a stage upon which the universe's play could unfold. To them, emptiness was simply an absence, like a missing piece of bread on the table. But as centuries passed, as science grew more careful in its experiments and more daring in its theories, that picture began to shift. Our journey tonight will begin by letting the idea of empty space settle into our minds slowly, like a breath in the dark. Because when we look at the vacuum with the eyes of modern physics, we find it buzzing with hidden activity. What seems like nothing turns out to be a frothing sea of possibilities, where particles appear and disappear in the blink of an eye, and the fate of entire galaxies might be tied to the energy hidden in this apparent emptiness. Let's take our first gentle step into that world. Picture yourself in a sealed chamber where all the air has been pumped out. The lights are dim, and your ears adjust to the silence. In the early days of science, that chamber would have been called a vacuum, a place utterly empty. To human senses, that's exactly what it feels like. But science has a way of peering deeper, of asking what lies beneath appearances. And when we peer into this emptiness with the tools of quantum mechanics, the silence is broken. The vacuum is no longer a simple void. It is restless, humming, alive in ways that defy ordinary thought. And so, as you drift with these words, remember that what we call nothing is not really nothing at all. It is the most mysterious something we know. When most of us hear the phrase empty space, the picture that comes to mind is usually quite straightforward. A bare room, a hollow jar, the gap between stars where no light seems to shine. emptiness feels simple, like the absence of anything at all. Yet in science, and especially in physics, that apparent simplicity is a little trap. What seems obvious turns out to be layered with mystery. Empty space is not so empty, and the journey to discover this truth has been one of the longest and strangest in human thought. It's easy to sympathize with the ancient view that nothingness was impossible. After all, whenever you try to create a pocket of emptiness in everyday life, something seems to rush in and fill it. Open a bottle underwater and bubbles immediately form to occupy the space. Open the door of a sealed room and air flows in at once. There's a natural intuition that emptiness cannot last, that nature doesn't tolerate it. For centuries this was considered common sense. Aristotle, one of the most influential philosophers of the ancient world, even argued that a true void could not exist. To him, space without matter was like a play without actors, meaningless and inconceivable. He believed motion itself required the presence of a surrounding medium. Without that, he said, objects could not move at all. So emptiness was not only impractical, it was nonsensical. Of course, human curiosity has never been satisfied with declarations. The question of whether emptiness could exist kept resurfacing, like a riddle that refuses to stay quiet. Centuries later, in the Middle Ages, scholars and theologians debated the possibility again. Some framed it in spiritual terms, imagining whether divine power could create a space that held absolutely nothing. Others approached it from a more physical angle, wondering whether air could be sucked away and leave behind true void. But it wasn't until the scientific revolution in the 17th century that experiments began to pull the curtain back. One of the earliest explorers of emptiness was Evangelista Torricelli, a student of Galileo. He invented the barometer, a device that used mercury in a glass tube to measure air pressure. What he discovered startled many of his contemporaries. When mercury was raised in the tube and left a gap at the top, that gap wasn't filled with air. It seemed to be genuinely empty. For the first time, scientists could point to a small pocket of space and say, here, perhaps, is a vacuum. Around the same time, Otto von Guericke, a German scientist and mayor of Magdeburg, carried out spectacular demonstrations of vacuum. He built powerful pumps to remove air from containers. In his most famous experiment, he sealed two enormous copper hemispheres together, pumped out the air between them, and then showed that teams of horses pulling in opposite directions could not separate the halves. The force holding them together wasn't glue or bolts. It was the weight of the atmosphere pressing in to fill the empty space. These public spectacles convinced many that emptiness could indeed be created, at least in a limited form. For a while, the vacuum was seen as just that, an absence. Nothing more than space where air had been removed. But as science advanced, new puzzles began to creep in. If space is empty, then how does light travel through it? In the 19th century, physicists were certain that waves needed a medium to propagate. Water waves travel through water, sound waves through air. Surely light must also have a medium. They imagined an invisible substance filling all of space, so delicate that it could not be touched or seen, but so pervasive that it supported the undulations of light. They called it the luminiferous ether, a grand term for what was supposed to be the hidden fabric of the void. For decades, scientists worked under the assumption that this ether filled empty space, that the void was not empty at all, but gently saturated with this strange invisible material. The idea seemed reasonable until experiments were designed to detect the ether directly. The most famous of these was the Michelson-Morley experiment in 1887. It tried to measure the motion of Earth through this supposed medium, like a ship moving through water. But the results were baffling. No matter how carefully they looked, they could find no sign of the ether. Light did not seem to care whether space was filled with a medium or not. It sped along at the same pace in every direction, as if the ether did not exist. This negative result would later become a cornerstone in the work of Einstein, who showed that light does not need a medium at all. Space itself, empty or not, was enough. At this point, the concept of emptiness had shifted again. It was no longer an absence waiting to be filled with mysterious ethers. It was a stage upon which matter and energy played, with no hidden substance beneath. But then came the revolution of quantum mechanics, and the floor gave way once more. In the quantum view, even a vacuum is not a simple void. It is restless, buzzing with activity. Particles flicker into and out of existence. Energy pulses unpredictably, sometimes adding to the void, sometimes subtracting from it, but never truly going away. This is perhaps the strangest turn of all, because it suggests that what we thought of as nothing is in fact seething with potential. It's worth pausing to notice how counterintuitive this is. If you walk into an empty room, you expect silence. If you open an empty jar, you expect nothing inside. The idea that even when you remove everything, there is still something left behind is hard to grasp. And yet experiments confirm it again and again. Empty space pushes on plates, shifts the behavior of atoms, and even seems to accelerate the expansion of the universe itself. What we call nothing is more active than the busiest city, though it hums at scales far beyond our ordinary perception. Think about the vast distances between stars. When you look up at the night sky, you see pinpricks of light scattered across a black canvas. That darkness appears empty, a void stretching in all directions. But the truth is that even in those great gulfs of apparent nothingness, the quantum vacuum reigns. Fields vibrate, particles pop in and out, and the very fabric of space-time may ripple. What looks like the loneliest desert may be richer than the most crowded marketplace, only hidden from view. This strange idea of empty space changes the way we think about reality itself. If emptiness is never truly empty, then the universe is never at rest. There is no place where nothing happens. Even in the coldest reaches of intergalactic space, far from any planet or star, the vacuum remains busy, quietly shaping the behavior of matter and energy. And that hum of nothingness may not just be background noise, it may be the very foundation of everything that exists. You might find yourself wondering what it means for our daily lives. Does this seething vacuum affect you as you lie in bed, listening to these words? The answer is both yes and no. On one hand, the fluctuations of empty space are so subtle and fleeting that they vanish before you could ever notice them. On the other hand, without them, atoms themselves might not exist. The stability of matter, the way particles interact, even the birth of the cosmos, may depend on the restless activity of the vacuum. So while you can't feel it directly, you are woven into it. You are built from it. The nothing that is everything runs through you like an unseen current. When we talk about empty space, then, we're not talking about a lifeless void. We're talking about a paradox, a place where nothing exists and yet everything begins. This shift from nothing as absence to nothing as fertile ground is one of the most profound transitions in human thought. It's no longer about whether the void exists, but about how much it contains, how much it contributes, and how much it defines the universe itself. The strange idea of empty space leaves us with a curious feeling. On one hand, it is humbling to realize that what we once dismissed as nothing is far richer than we imagined. On the other hand, it is comforting, because it means the universe is never empty, never silent, never without motion or possibility. Even in the spaces between stars, between atoms, even in the pause between your breaths, something is always happening. And that restless undercurrent of existence will be our companion as we continue to explore deeper into the mysteries of the vacuum. If the idea of empty space feels strange to us today, imagine how it must have seemed thousands of years ago. Long before telescopes, microscopes, or vacuum pumps, people tried to picture what it would mean for there to be nothing at all. They did not have the vocabulary of atoms, fields, or quantum fluctuations. They had only their senses, their imagination, and their arguments. And from these, a set of ideas began to form that would echo through philosophy and science for centuries. For many early thinkers, the world was full, not empty. Everything had to be made of something, and if there was a gap, it was only waiting to be filled. The Greek philosopher Parmenides, writing in the 5th century BCE, took an uncompromising stance. He claimed that nothing cannot exist, because to speak of nothing is to speak of something. In his reasoning, the very act of naming or describing emptiness makes it into a kind of being, which is a contradiction. To him, existence was a continuous whole, a solid reality with no gaps, no void, no nothingness at all. His rival in thought, Democritus, painted a different picture. He was one of the first to suggest that the world is made of indivisible particles, which he called atoms, moving through empty space. For Democritus, the void was not only real but necessary. Without empty space, he argued, atoms would have nowhere to move, no room to rearrange into the forms that make up matter. The universe, in his view, was a grand dance between two things only: atoms and the void. This was a daring idea, one that ran against the common sense of his time. Most of his contemporaries found it unsettling. How could something as intangible as nothingness be considered real? And yet that seed of thought would one day become the cornerstone of modern science. Between these poles of thought, other voices joined the debate. Aristotle, as mentioned earlier, insisted that nature abhorred a vacuum. He reasoned that in a void there would be no medium to resist motion, which would make movement instantaneous and infinite, an absurd result. To avoid this, he concluded that the void could not exist. The universe must always be filled with some substance, whether air, water, fire, or the mysterious quintessence he believed made up the heavens. This view held sway for nearly 2,000 years, shaping how people thought about physics, cosmology, and even theology. Meanwhile, outside the Greek world, other traditions wrestled with similar questions. In ancient India, philosophers of the Vedic and later Buddhist schools pondered the concept of shunyata, often translated as emptiness. Unlike the Greek focus on physical space, this was a more subtle and layered notion. Emptiness in this context referred to the absence of inherent existence, the idea that things have no fixed essence, only relationships and conditions. To call something empty was not to say it did not exist, but to say it did not exist in the way we might assume. It was a perspective less about the vacuum of physics and more about the fabric of reality itself, still deeply tied to the way human beings perceive and construct the world. In China, Taoist philosophy introduced another layer. The Tao Te Ching, attributed to Laozi, speaks often of the usefulness of emptiness. A clay pot is valuable not because of the clay, but because of the empty space it encloses. A room is useful because of the void inside it, not because of the walls alone. Here emptiness was not feared or denied, but embraced as something practical, even essential. The absence of matter was not a defect, but a feature. It gave form and function to what existed. In that sense, Taoist thought anticipated a truth that science would much later uncover. Emptiness has power, not despite its nothingness, but because of it. As centuries passed, the conversation about nothingness became entangled with religion and metaphysics. In medieval Europe, theologians argued about whether God could create a void. Some said omnipotence required the possibility. Others held firm that nothingness was meaningless, that creation itself filled every corner of existence. These debates were not idle. They influenced how scholars approached natural philosophy, the precursor to science. If emptiness was possible, then experiments to create or measure it made sense. If it was impossible, such efforts were foolish. By the time of the Renaissance, curiosity began to shift from pure philosophy to practical investigation. Scholars like Galileo and Torricelli were heirs to a long tradition of debate about nothingness. They inherited the skepticism of Aristotle, the daring of Democritus, and the metaphors of Taoists and Buddhists, even if only indirectly. What they attempted was to test the void, to see whether emptiness could be coaxed into existence not just as an idea, but as a physical reality. The experiments with vacuums, barometers, and air pumps were the hands-on answers to questions that had lingered for 2,000 years. It's remarkable to consider how far the human mind travelled before even touching real emptiness. For millennia, people argued about the void without any means to prove or disprove it. They sat under starlit skies, carved their ideas into scrolls, debated in dusty courtyards, and spoke of nothingness with the same seriousness as life and death. And in a way, they were right to do so. Even now, with all our instruments and equations, we find ourselves circling back to the same fundamental puzzle. Can nothing exist? Or is it always a mask for something deeper, something unseen? If you reflect on your own experience, the idea of nothingness remains slippery. Close your eyes in a dark room, and you still hear your heartbeat. Feel the weight of your body, sense the air moving in and out of your lungs. Even when deprived of sight and sound, there is still something. Try to imagine absolute nothingness. No light, no sound, no space, no time. It's almost impossible. The human mind craves content. It struggles to picture a void without filling it with darkness or silence, which are themselves something. Perhaps this is why philosophers argue so fiercely. Nothingness resists imagination. It feels like trying to hold water in a clenched fist. Yet in this very difficulty lies a clue. Maybe emptiness is not truly about the absence of things, but about the conditions that allow things to be. The clay pot, the empty room, the pause in a piece of music. These show us that nothing can be just as meaningful as something. In science too, we have learned that the vacuum is not barren but fertile. Not a blank stage, but a participant in the drama of existence. The ancient arguments, while incomplete, carried the seeds of this truth. When you think about the night sky again, about those spaces between stars, you're seeing the modern version of an ancient riddle. The Greeks asked whether the void was real. The Taoists asked what emptiness was good for. The Buddhists asked whether things had essence at all. And all of them, in their own way, pointed toward the paradox that science still grapples with today. Nothingness is not nothing. It is possibility. It is relationship. It is the quiet hum beneath being. As we let these thoughts drift, it's worth noticing how the story of nothingness has always walked hand in hand with the story of everything. You can't describe what exists without also describing what doesn't. You can't talk about fullness without emptiness. And so, from the earliest debates to the experiments of early modern science, the notion of nothingness has been both a challenge and an invitation. It invites us to stretch our imagination, to test our logic, and to build instruments that probe the edges of what we can sense. It whispers that behind what we see, there is always more to consider. The question of emptiness never left the minds of those who thought most deeply about existence. After all, to ask whether the void is real is to ask what kind of world we live in, and even what it means for something to exist at all. Across centuries and cultures, philosophers return to the same puzzle, turning it over like a stone in their hands, looking for its hidden facets. They wrote long treatises, argued in crowded halls, and whispered to their students about what lay beyond appearances. Their disagreements were fierce, but the persistence of their attention shows just how central the idea of nothingness was to their understanding of reality. In ancient Greece, the void divided entire schools of thought. Parmenides, with his vision of an unbroken, continuous existence, could not tolerate the notion of nothing. He believed that only what is can be spoken of, and what is not cannot be. If you say that nothing exists, you have already given it being by naming it, which makes it no longer nothing. This logical trap led him to conclude that reality must be solid, eternal, unchanging, without gaps or absence. Change itself, he argued, was an illusion, a trick of perception. It's hard for us now to imagine living by such a vision, but it was deeply compelling to those who believed that logic was the surest guide to truth. Democritus and Leucippus, by contrast, insisted that the void was not only real but indispensable. To them, the universe consisted of countless tiny indivisible atoms moving through empty space. Without the void, these atoms would be locked in place, unable to rearrange, unable to combine into the variety of forms we see. The void gave freedom of motion, and that freedom allowed complexity. Their view was not only physical but almost poetic. The dance of atoms in the void was the source of everything, from stars to soil to souls. While later thinkers dismissed this as speculative, the echoes of their argument are still with us, because in many ways, modern physics vindicated them. Between these extremes stood Aristotle. He could not accept that a void might exist, because he thought it would undermine the very laws of motion. In his reasoning, if there were empty space, an object could move infinitely fast since nothing would resist it. That, he felt, was absurd, so he declared the vacuum impossible. Nature, he said, abhors a vacuum, and wherever emptiness tries to appear, matter will rush in to fill it. For centuries, this pronouncement held enormous sway. Scholars repeated it as if it were a law of nature itself. For nearly 2 millennia, the belief that the void was impossible dominated Western thought. But elsewhere, other traditions approached the puzzle differently. In the schools of Buddhism, emptiness was not a flaw or impossibility, but a truth of existence. The term shunyata did not mean a physical vacuum, but rather the absence of intrinsic essence. Everything exists in dependence on conditions, they taught. To say something is empty is to say it cannot exist on its own, isolated and permanent. Instead, all things are interdependent, transient and relational. Emptiness here was not frightening, but liberating, a recognition that clinging to fixed notions of being leads to suffering. This was a very different kind of philosophy, but in its own way, it wrestled with the same question. In China, Taoist thinkers reflected on emptiness with a practical lens. The usefulness of the empty was a recurring theme. A wheel works because of the hollow hub at its centre. A room is livable because of the space inside it. Emptiness gave form, shape, and function to things. Laozi wrote that we mould clay into a vessel, but it is the emptiness inside that makes it useful. To them, the void was not something to deny, but something to embrace. It was the counterpart to fullness, the silence that makes music possible, the pause that gives rhythm to speech. This way of thinking softened the fear of nothingness, turning it into a partner of existence rather than its opposite. As the centuries advanced into the medieval period, the wrestling with void took on new colours. In the Islamic Golden Age, scholars like Alhazen, Avicenna and Averroes studied Aristotle closely, but they also questioned him. Could a vacuum exist in principle, even if nature tended to fill it? Experiments with air pressure, light and optics led some to cautiously entertain the idea that emptiness might be more than a theoretical curiosity. These questions reached into Europe as well, where Christian theologians debated whether God, in his omnipotence, could create a space entirely devoid of matter. If omnipotence meant truly unlimited power, then surely even a void must be possible. On the other hand, if emptiness was incoherent by definition, then even divine power could not produce it. What began as a question of physics became a theological puzzle, wrapped in questions of divine will and logical consistency. When the Renaissance arrived, and with it the rebirth of experimental science, the old philosophical wrestling matches took on practical form. Galileo, Torricelli and Boyle did not simply speculate about emptiness, they built apparatus to test it. The void moved from argument to experiment, from parchment to laboratory. Yet the philosophical background never disappeared. The debates of Aristotle and Democritus still lingered behind the scenes, shaping how scientists interpreted their results. Was emptiness a mere absence? Or was it something more? A canvas upon which forces could act? These were not questions that experiments alone could answer. They demanded thought, interpretation, and the kind of conceptual wrestling that philosophy had always provided. Even in the modern world, philosophers have not abandoned the void. In the 20th century, with the rise of relativity and quantum mechanics, They found themselves returning to the ancient puzzle in new language. If space itself can bend and warp, is it really empty? If quantum fields buzz with virtual particles even in a vacuum, is there such a thing as nothing at all? Some philosophers of science argue that the vacuum is not absence, but a field with its lowest possible energy, a something that masquerades as nothing. Others contend that calling it nothing is misleading, that our language itself is at fault. The wrestling continues, not with robes and scrolls, but with journals and conferences, still circling the same elusive question. What makes this struggle so enduring is that nothingness touches both logic and imagination. Logically, it seems impossible to conceive of absolute nothing. If you imagine it, you've already given it qualities: darkness, silence, vastness. Imagination cannot tolerate a blank without turning it into something. At the same time, physics suggests that what we call nothing is never truly empty. The vacuum seethes with energy, fluctuations, and possibilities. So the philosopher and the scientist meet again, both wrestling with the same paradox, one through reasoning, the other through measurement. As you let these ideas settle, notice how familiar they feel even in daily life. We talk about having nothing to do, yet there are always small tasks waiting. We say a room is empty, but dust, light, and warmth still linger there. We say our minds are blank, but thoughts hover at the edges waiting to intrude. True nothingness always seems to slip away, replaced by traces of something. Perhaps this is why philosophers have wrestled so long. Nothingness is like a horizon, always ahead but never reached. And so the wrestling with the void continues. It has passed from Parmenides to Democritus, from Aristotle to Buddhist monks, from medieval theologians to modern physicists. Each generation takes its turn, grips the puzzle, and tries to pin it down. None succeed completely, but each leaves marks, insights, and metaphors that carry forward. The void resists capture, yet it compels attention. It is absence, but an absence so provocative that it becomes the most persistent presence in philosophy. And as we drift further into the story of the vacuum, this long tradition of wrestling will remain with us, whispering reminders that what we call nothing is never simple, and perhaps never quite what we think. By the time Isaac Newton was born in the middle of the 17th century, the old debates about nothingness had been simmering for 2,000 years. Philosophers had argued, theologians had speculated, experimenters had tinkered with pumps and tubes, and yet the question of what fills the space between things remained unsettled. Into this world of uncertainty arrived a man whose way of thinking would redefine not only physics, but also the very stage upon which the universe seemed to rest. Newton's vision of space and time gave the void a new identity. It was no longer simply the absence of matter, no longer a philosophical curiosity. It became a framework, a container, a still backdrop against which the drama of the cosmos unfolded. When people speak of Newton today, they often mention the falling apple or the laws of motion, the familiar stories told in classrooms. But underneath those ideas lay a picture of the universe that was radical for his age. To Newton, the world was mechanical, orderly, predictable, a system of forces and motions that could be described with mathematics. But such a system required a stage, a place where motion occurred, a grid against which position and velocity could be measured. That stage, in his mind, was absolute space, and running through it, flowing without pause, was absolute time. Imagine space as an infinite still ocean, perfectly calm, extending without boundary in every direction. On this ocean float all the stars, planets, and particles of matter. They may move, they may collide, they may spin and tumble, but the ocean itself does not ripple. It simply exists, silent and unchanging, holding everything in place. This was Newton's void, not a seething quantum vacuum, not an abstract philosophical absence, but a serene, eternal arena. Between the stars stretched not mystery, but stillness. a canvas so smooth and uniform that every calculation could be made upon it. This picture had tremendous power. For one thing, it made sense of motion in a new way. Aristotle had argued that motion required resistance, that without a medium there could be no movement. Newton swept that aside. Objects, he said, did not need resistance to move. They needed only inertia. In absolute space, if no force acted upon a body, it would continue in uniform motion forever. This was a startling idea at the time. It meant the void was not an obstacle or impossibility, but the very condition that made endless motion possible. The stillness between the stars became not frightening but reassuring. It allowed the planets to orbit, comets to sweep across the sky, and apples to fall in ways that could be calculated and predicted. In Newton's hands, emptiness was not an absence of meaning but a foundation of order. His equations worked because space and time themselves were steady, dependable, immune to change. The void was not chaotic, it was absolute. To understand how deeply this shifted thought, consider how people before Newton had struggled with the heavens. The planets wandered unpredictably against the background of stars, sometimes moving forward, sometimes backward, their paths hard to reconcile. Many believed that crystalline spheres or guiding intelligences were required to explain such motion. Newton dissolved all of that with a single framework. Gravity pulled, inertia carried, and absolute space provided the stage on which these interactions played out. Suddenly, the wandering of the planets was no longer mysterious. It was a consequence of forces acting in an empty arena. Of course, not everyone agreed. The philosopher Gottfried Wilhelm Leibniz, Newton's great rival, resisted the idea of absolute space. To him, space was not a thing in itself, but a set of relations between objects. Without matter, he argued, space had no meaning. Why postulate an infinite container if no one could ever experience it directly? For Leibniz, the void was a mathematical convenience at best, a fiction at worst. Newton disagreed passionately. In his mind, space and time were as real as the matter that moved through them. They existed independently, flowing and extending regardless of what occupied them. This was not just metaphysics to him. It was the backbone of his physics. The debate may sound abstract, but it shaped how generations of scientists thought about the cosmos. Newton's absolute space became the dominant picture, not least because it worked so well. His mechanics predicted eclipses, tides, and trajectories with uncanny accuracy. Sailors used his formulas to navigate oceans, engineers used them to design bridges and machines, astronomers used them to chart the heavens, and underneath it all lay the still void, the silent arena, the absolute nothingness that was somehow everything. It's worth pausing here to imagine what it felt like to live under Newton's universe. The world seemed vast but knowable, infinite but ordered. The stars were no longer lights nailed to crystalline spheres, but suns moving through endless darkness. The Earth was no longer the fixed centre, but a planet circling the sun, itself circling within a galaxy, itself drifting through the vast calm of infinite space. The scale was staggering, but the order was comforting. Between the stars lay emptiness, yes, but emptiness that provided stability. In Newton's vision, the cosmos was a grand machine, and the void was its casing. This picture also carried subtle philosophical consequences. If space and time were absolute, then they existed even if no matter did. Imagine, Newton would say, a completely empty universe, no stars, no planets, no particles. Still, there would be space stretching without bound. Still, there would be time ticking relentlessly forward. Existence did not depend on content. It depended on the stage. To Newton, this was self-evident. To his critics, it was absurd. But the power of his mathematics silenced many objections. The void had become respectable, even essential. And so, the stillness between the stars became one of the most enduring images of science. For more than 2 centuries, Newton's universe reigned. It guided explorers, inventors, and dreamers. It shaped the Enlightenment belief in reason, order, and progress. It reassured people that beneath the chaos of life lay a steady, predictable structure. Emptiness was no longer terrifying. It was the quiet, dependable backdrop of reality. Yet even in Newton's time, cracks in the vision began to appear. The question of action at a distance troubled many. How could gravity pull across emptiness without any medium? Did not forces require a carrier? Newton himself admitted discomfort with this, famously saying he did not feign hypotheses. He described gravity mathematically, but left its mechanism mysterious. Still, his universe of stillness between the stars endured, because it worked. The planets obeyed, the comets obeyed, the tides obeyed, and humans, eager for order, embraced the void as their silent ally. When you look up at the night sky, imagine it as Newton might have. Between each star lies not an ether, not a swirl of unseen activity, but pure stillness. A void stretching endlessly, identical in every direction, steady and absolute. The stars are like lanterns hung in a vast hall, their light shining across the empty expanse. The hall itself does not move, it does not change, it simply is. Against such a backdrop, the laws of motion make sense, and the dance of the cosmos becomes comprehensible. That was the power of Newton's vision, and yet, as history moved forward, other voices would rise again to question it. Was the void really still? Was space truly absolute? Could emptiness exist without content? The next centuries would bring revolutions that shook Newton's serene stage, bending and warping it until stillness gave way to dynamism. But for a long time, the idea of absolute silent space reigned supreme. It was the stillness between the stars, and it carried humanity from the age of horse-drawn carriages into the age of steam, from candlelight to gas lamps, from maps drawn by hand to charts guided by Newton's calculus. As you drift with these thoughts, notice how the void has changed shape in our story. For the ancients, it was impossible, a logical absurdity. For Newton, it became real, absolute, and necessary. The stillness between the stars was no longer frightening but a comfort, a promise of order in a vast and sometimes confusing universe. And though later science would show that the void is far stranger than Newton ever imagined, his vision still lingers. In everyday life, when we say space is empty, we echo Newton. When we picture stars shining in the blackness, we are still living in his universe. For more than 2 centuries after Newton, the universe seemed like a vast machine ticking steadily in silence. Space was absolute, time was universal, and the void between the stars was a calm, unchanging backdrop. Astronomers charted orbits, engineers built machines, and explorers sailed oceans with Newton's equations as their guide. But by the late 19th century, cracks began to appear in this serene picture. Strange results from experiments hinted that something was missing. The stillness between the stars might not be as still as everyone thought. When Albert Einstein entered the scene at the start of the 20th century, the void began to change shape again. He was young, working at a patent office in Bern, far from the prestigious universities of Europe. Yet his way of thinking was fresh, unburdened by tradition. In 1905, he published papers that transformed physics, and among them was his special theory of relativity. With it came a simple but radical idea. The laws of physics are the same for all observers, and the speed of light is constant no matter how you move. These 2 principles overturn the old certainty of absolute space and absolute time. In Newton's universe, everyone agreed on what now meant. Time ticked the same everywhere, independent of the observer. But in Einstein's world, simultaneity was relative. Two events that seem to happen at the same time for one observer might happen at different times for another, depending on their motion. The flow of time itself became flexible, and space too was no longer an unmoving grid. It was bound together with time in a single entity, space-time. The void between the stars was not a silent hall but a fabric, woven and interconnected, stretching and bending with the presence of mass and energy. This was not just a mathematical trick. It changed the way scientists thought about the universe at its core. Imagine laying a heavy ball on a stretched rubber sheet. The sheet dips and curves around the ball, and smaller marbles placed nearby roll toward it, not because the ball reaches out to pull them, but because the sheet itself is warped. That, Einstein suggested, is how gravity works. Mass and energy bend space-time, and objects follow the curves. There is no need for mysterious forces acting at a distance. The void itself is dynamic. It responds, it shapes, it guides. The idea was strange but beautiful. It meant that space was not empty at all. It had properties, geometry, and behaviour. The still stage of Newton's cosmos was replaced by a flexible fabric. Stars did not simply shine in the darkness. They pressed into the very structure of space-time, sculpting valleys and hills that guided planets and light alike. The universe was no longer built upon an indifferent backdrop. The backdrop itself was alive. Einstein's theory soon expanded into what became known as general relativity, published in 1915. It went beyond special relativity, which dealt with uniform motion, to describe how gravity itself is a manifestation of curved space-time. The equations were complex, but their meaning was profound. Mass tells space-time how to curve, and curved space-time tells mass how to move. The void had become an active participant in the cosmos. Evidence came quickly. In 1919, during a solar eclipse, astronomers measured the positions of stars near the Sun. According to general relativity, the Sun's mass should bend the path of light, shifting the apparent positions of stars. The measurements confirmed it. Light itself bowed to the curvature of space-time. Headlines declared Einstein a genius, and the world glimpsed a new picture of reality. The void was not empty. It was a fabric that could be warped, stretched, and reshaped. This fabric also carried with it new possibilities. If space-time could bend, it could also ripple. Gravitational waves, Einstein predicted, would spread outward when massive objects moved violently, like ripples in a pond. For a century they remained hypothetical, too faint to detect. But in 2015 detectors finally caught them, the faint murmurs of colliding black holes. Once again, the void revealed itself not as silence but as soundless vibration, the universe itself ringing with events that shook space-time to its core. As strange as this seems, it fits into a long tradition. Philosophers had wrestled with whether emptiness was possible. Newton had granted it absolute existence but stripped it of activity. Einstein brought it to life again. Space was no longer just where things happened. It was part of the happening. It had its own dynamics, its own energy, its own role to play. The fabric was not a background but an actor in the story. Think about what this means for the night sky. When you look at the stars, you're not seeing them scattered across a blank canvas. You're seeing them embedded in a flexible fabric. Each one makes a dimple in space-time, bending the path of light, influencing the motion of its neighbours. The galaxy itself curves the space-time around it, holding stars in their orbits. Even empty intergalactic space, far from visible matter, is not empty. It is space-time with structure and geometry, shaped by what lies within it. This vision also changed how scientists thought about the universe as a whole. If space-time could curve, then perhaps the cosmos was not static. Perhaps it expanded or contracted. Indeed, solutions to Einstein's equation suggested just that. Later observations confirmed that galaxies are receding from one another, that space itself is stretching. The void, far from being empty and still, is swelling, carrying galaxies along like raisins in rising dough. What we once called nothing is expanding, reshaping the destiny of everything within it. Einstein himself wrestled with these implications. At first, he resisted the idea of an expanding universe. He introduced a cosmological constant, a term in his equations to hold the cosmos steady. But later, when evidence showed expansion was real, he reportedly called the constant his greatest blunder. Ironically, modern cosmology revived it as dark energy, a mysterious force driving accelerated expansion. Once again, the void proved itself anything but simple. What's striking in all this is how much our picture of emptiness has changed. In Newton's hands, the void was calm and absolute, a stage set for the play of matter. In Einstein's, it became a fabric, flexible and dynamic, shaping the play itself. And even that was not the final word, because the quantum world would soon reveal a deeper strangeness, that the fabric is filled with restless fluctuations, particles popping in and out, energy shimmering in the very definition of vacuum. But before we reach that, it's worth letting Einstein's insight sink in. Nothing is not nothing. The fabric between the stars bends, stretches, vibrates, and grows. It is not silent but resonant, not static but alive. The fabric that isn't empty is more than a scientific idea. It reshapes how we think about our place in the universe. If space itself is active, then we are not just floating in a void. We are woven into a cosmic cloth that responds to us even as we respond to it. Every movement of mass, every flicker of energy leaves an imprint. The universe is not a play on a stage. It is the stage and the play at once, inseparable and dynamic. And that realization, as Einstein showed, changes everything. By the early 20th century, Einstein had bent space and time into a fabric, turning the silent void of Newton into something dynamic. But just as people were beginning to absorb this vision, another revolution was stirring. It was smaller in scale, but stranger in spirit. While relativity reshaped the cosmos at the largest levels, quantum theory crept in from the smallest, from the hidden world of atoms and their subatomic parts. Together, these revolutions would collide and mingle, leaving behind a picture of reality more unsettling than anything philosophers had dared imagine. And at the heart of it was the discovery that even the so-called vacuum is not empty, but alive with invisible fields. The story began with simple puzzles. At the dawn of the 20th century, scientists thought they understood atoms well enough. Electrons orbited nuclei like planets around the sun. Light was a wave moving through space. Heat and energy followed neat laws of thermodynamics, but cracks began to show. Experiments revealed that light sometimes behaved like a particle, sometimes like a wave. Electrons, too, seemed to act in ways no classical picture could explain. The old machinery of Newtonian physics could not account for the strange results that kept appearing in laboratories. In 1900, Max Planck made a proposal that seemed modest at first, but would open the door to a new era. To explain the spectrum of radiation emitted by heated objects, he suggested that energy came in discrete packets, quanta, rather than flowing in a smooth, continuous stream. His idea was initially treated as a mathematical trick, a way to fit equations to data. But soon, it became clear that quanta were not just bookkeeping, they were real. Energy itself was granular, lumpy, indivisible at the smallest scales. Einstein pushed the idea further in 1905, when he explained the photoelectric effect, showing that light could knock electrons out of metal only if it arrived in discrete packets, later called photons. Light was not just a wave, but also a particle. The duality baffled intuition. How could something be both? Yet experiment after experiment confirmed it. The universe was playing by rules no one had expected. As the years went on, quantum mechanics took shape. Niels Bohr, Werner Heisenberg, Erwin Schrödinger and others developed frameworks to describe the odd behavior of particles. probabilities replace certainties. The path of an electron could not be traced like a tiny billiard ball, but only described as a cloud of possibilities. Measurements no longer revealed what was there all along, but seemed to help determine what became real. This new physics was unsettling, but it worked. Atoms, once mysterious, began to yield their secrets. Yet beneath these developments lay a deeper shift. If particles were not little points moving in empty space, then what were they? The answer slowly emerged. They were excitations of fields. Imagine space not as a void, but as filled everywhere with invisible fields, each one corresponding to a type of particle. An electron is not a tiny bead drifting in nothingness. It is a ripple in the electron field that stretches across the universe. A photon is not a bullet of light shot through emptiness. It is an excitation of the electromagnetic field. In this view, the vacuum is not barren at all. It is the lowest state of these fields, still humming even when no particles are present. This new framework became known as quantum field theory. It was not born overnight, but assembled piece by piece through the first half of the 20th century. Schrödinger's wave mechanics, Heisenberg's matrix mechanics, and Paul Dirac's relativistic equations all fed into it. Dirac in particular revealed that the mathematics of fields predicted not only known particles, but also their opposites, antimatter. Suddenly, the vacuum was not just a stage but a generator of possibilities. It could spawn pairs of particles and antiparticles fleetingly before they annihilated each other back into nothingness. Think of what this means for emptiness. In Newton's world, the void was stillness. In Einstein's, it was fabric. In the quantum view, it became a restless sea. Even when stripped of all matter, even at its lowest energy, space is filled with invisible fields, all vibrating, all capable of producing particles under the right conditions. The vacuum is not absence but presence at its quietest. This picture, though abstract, finds support in experiment. Consider the Casimir effect, first predicted in 1948. Place two metal plates very close together in a vacuum, and they will feel a tiny force pulling them together. No particles are between them, and yet something pushes. The explanation lies in the quantum fields. Even the vacuum buzzes with fluctuations, virtual particles appearing and vanishing. Between the plates, only certain fluctuations fit. Outside, all kinds of fluctuations occur. The imbalance produces pressure, nudging the plates together. What looks like nothing becomes measurable, a force born from emptiness. Quantum fields also explain how forces operate. The electromagnetic field gives rise to photons that carry electric and magnetic interactions. The strong field binds quarks into protons and neutrons. The weak field governs radioactive decay. The Higgs field, discovered experimentally in 2012, gives mass to particles through its ever-present interaction. These are not distant, occasional influences. They are the fabric of reality itself, woven into the vacuum. It's tempting to imagine fields as ethereal substances filling space, but that analogy only goes so far. They are not fluids or gases. They are mathematical descriptions of how the universe behaves, real in their effects but elusive to our senses. You cannot scoop a jar of the electron field or bottle up the Higgs field, and yet without them, no particles, no atoms, no stars, no listeners would exist. The vacuum fields make everything possible by never being truly nothing. What is most striking is how this picture blurs the line between something and nothing. A particle is simply a field in an excited state. The vacuum is that same field in its ground state. They are not separate entities, but two faces of one underlying reality. Nothingness and somethingness become points along a continuum, not opposites. The emptiest space imaginable is still thick with hidden structure, waiting to reveal itself. For everyday life, this strangeness is invisible. You don't notice the quantum fields humming as you walk through a room or sip tea. Yet every atom in your body depends on them. The stability of matter, the chemistry of life, The very possibility of solid objects arises from quantum fields filling space. You are built from excitations of fields. In that sense, you are woven from the same fabric as the vacuum itself. The birth of quantum fields did not resolve every mystery. In fact, it raised new ones. What exactly is the vacuum energy of these fields? Why does the mathematics suggest it should be infinite, yet the universe behaves otherwise? What does it mean for virtual particles to appear and vanish if we can never catch them directly? These questions remain open, fueling both physics and philosophy. But one thing is clear: the void is not empty. The birth of quantum fields replaced silence with a chorus, invisible but constant, humming beneath everything. As you let these thoughts drift, imagine space not as a hollow container but as an ocean, its surface smooth when calm but always ready to ripple. Every particle is a wave, every interaction a disturbance. Even when the ocean seems perfectly still, currents swirl beneath, unseen but real. That is the vacuum of quantum field theory, and from that restless ocean, the universe as we know it arises. Once the language of quantum fields took root, the idea of emptiness could never again return to what it once was. The vacuum was no longer a passive background, no longer a silent sheet stretched under the stars. It had become restless, alive in ways our senses could not detect, filled with potentiality rather than void. And one of the strangest consequences of this shift was the realization that particles themselves could appear, uninvited and unannounced, only to vanish again a heartbeat later. Physicists call these ghostly appearances quantum fluctuations. The term sounds delicate, as though nothing dramatic were happening, but the reality is both strange and profound. In the vacuum, particles can pop into existence in pairs, one particle and its antiparticle twin, borrow a bit of energy from the universe, and then annihilate one another before that energy debt must be repaid. To human intuition, it seems impossible. We're used to a world where something does not simply emerge from nothing. A chair does not appear in the middle of the room and vanish before we can sit on it. Food does not materialize on an empty plate and then dissolve back into nothingness. But in the quantum vacuum, this flickering is not only possible, it is inevitable. The rules behind this odd behavior are not arbitrary. They are bound by one of the most famous principles in physics, the uncertainty principle, formulated by Werner Heisenberg. It says in part that certain pairs of quantities cannot be known precisely at the same time. For example, you cannot pin down both the exact position and the exact momentum of a particle. The more you know of one, the less you know of the other. The same idea applies to energy and time. Over very short periods, energy can fluctuate, briefly violating conservation, as long as the books are balanced quickly afterward. The universe allows these momentary borrowings, like a strict banker who looks the other way if the debt is repaid instantly. These fluctuations mean that the vacuum is never perfectly calm. It is seething with activity, particles bubbling in and out, a quantum foam at the smallest scales. They are not particles in the ordinary sense, not stable or detectable in isolation, but they have real effects. The Casimir effect, which we touched on earlier, is one example. Another lies in the corrections to the magnetic properties of electrons. Virtual particles, as they are often called, swarm around real ones, shifting their behavior slightly. The predictions of quantum electrodynamics, the theory describing this, match experiments to astonishing precision, better than 1 part in a trillion. That accuracy is possible only because the vacuum is not empty. It is full of fleeting presences that alter reality, even as they remain uncatchable. Imagine, if you will, looking into a dark, still pond at night. To the eye, its surface seems calm, mirror-like, but beneath, fish dart, currents swirl, tiny insects disturb the water's skin. The vacuum is much like that pond. On the surface, it appears empty, silent, but beneath, invisible motions stir ceaselessly. What we call nothing is alive with activity, only hidden from casual view. The implications stretch across physics. Consider black holes, those enigmatic regions where gravity grows so strong that not even light can escape. For decades, they were thought to be perfect prisons, swallowing all information. But in the 1970s, Stephen Hawking showed that quantum fluctuations near the event horizon lead to radiation. A particle-antiparticle pair forms just at the edge. Normally they would annihilate, but if one falls into the black hole while the other escapes, the escaping particle becomes real. The black hole loses a tiny bit of mass, radiating energy into space. This process, now called Hawking radiation, means black holes can eventually evaporate. It is a breathtaking result. The most massive, voracious objects in the cosmos slowly fade away because the vacuum itself never stays quiet. Another consequence lies in the very expansion of the universe. Cosmologists suspect that in the earliest fractions of a second after the Big Bang, quantum fluctuations in the vacuum were stretched by cosmic inflation, magnified to cosmic scales. Those tiny flickers became the seeds of galaxies. The very structure of the cosmos, the clusters and voids of galaxies we see today, may owe their existence to particles that popped in and out of nothing more than 13 billion years ago. In this sense, the vacuum is not just restless, it is creative, shaping the universe itself. Of course, one must be careful with language. These particles are not real in the way ordinary matter is. They are virtual mathematical entities that make sense only within the framework of quantum field theory. They cannot be bottled or weighed, yet their influence is measurable, as precise experiments have shown time and again. They are the whispers of the vacuum, fleeting and insubstantial, but never irrelevant. This behavior challenges our intuitions about cause and effect, about being and non-being. Philosophers wrestled for millennia with the notion of nothingness, often declaring it impossible. Quantum mechanics does not banish nothing but transforms it into a restless medium. The old question, can something come from nothing, takes on a new shape. In one sense, no, because the vacuum is not truly nothing. In another sense, yes, because even in its lowest state it produces transient somethings. The border between nothing and something becomes porous, blurred by the constant flickering of the quantum world. Even technology relies on this. The transistors that power your phone, the lasers that scan barcodes, the superconductors that promise new horizons, all depend on quantum principles shaped by fluctuations in fields. The restless vacuum is not only a philosophical curiosity, it is the quiet foundation of the modern world. If you sit quietly and reflect, you might notice how this mirrors our own experience. Even in moments when life feels still, when you imagine your mind is blank, thoughts flicker at the edges. Images appear unbidden, dissolve and reform. Silence is never perfect silence. The body hums, the breath continues, the heart beats. Emptiness is never quite empty. In that way, the vacuum is strangely familiar. It reflects a truth we sense in ourselves. Stillness always conceals motion, and nothingness always hides something. Physicists sometimes joke that the vacuum is the most expensive nothing you can imagine, because its energy is both infinite in theory and priceless in consequence. Calculations of vacuum energy often diverge wildly, suggesting impossibly large values, while the observed universe behaves in far gentler ways. Reconciling these differences remains one of the deepest puzzles in physics, a reminder that the vacuum, with all its flickering particles, still holds mysteries unsolved. Particles popping in and out of nowhere are not trivial accidents. They are the signature of a universe where emptiness itself cannot sit still. They remind us that nothingness is not absence but possibility, that the void is fertile ground, not barren wasteland. They whisper that what we call nothing may, in fact, be the most profound something of all. By now, our journey through the vacuum has revealed that what seems to be nothing is not silent at all. Particles flicker in and out, energies shift and settle, and the very emptiness of space is restless. But to understand why, To see how the universe allows such strangeness, we need to sit with one of the most unsettling and misunderstood principles in all of physics. It was proposed by Werner Heisenberg in 1927, and though it is often reduced to a slogan about measurement, its consequences go far deeper. It is the uncertainty principle, and it is the trick at the heart of the quantum vacuum. In the everyday world, we assume things can be known precisely. If you throw a ball, you can in principle measure where it is and how fast it is going. If you park your car on a street, you know both its position and, if it is standing still, its momentum. But the quantum world resists such clarity. Heisenberg's principle says that certain pairs of quantities cannot be pinned down with unlimited accuracy. The more precisely you know one, the less precisely you can know the other. It is not a matter of better instruments or cleverer techniques, it is woven into reality itself. The most famous pair is position and momentum. Momentum is a measure of motion, the product of mass and velocity. At the quantum level, if you try to measure a particle's position with perfect accuracy, its momentum becomes uncertain. If you try to nail down its momentum exactly, its position becomes fuzzy. The product of those uncertainties is never zero. There is always a limit. Reality refuses to be nailed down in both ways at once. To see why, it helps to think in terms of waves. A particle in quantum mechanics is not a little dot, but is described by a wave function, a spread of possibilities. If you want to know a particle's position exactly, you need a wave very tightly localized, like a sharp spike. But to make such a spike, you need many different waves of different momenta interfering together. The more localized the wave, the wider the spread of momenta it requires. Conversely, if you want a single clear momentum, you need a pure wave of definite wavelength, which by its nature spreads out across space. You cannot have both at once. This interplay leads to an odd truth. At the smallest scales, particles are never at rest. Even when cooled to absolute zero, the lowest possible temperature, atoms still jiggle slightly. This zero-point motion is a direct consequence of the uncertainty principle. If an atom were perfectly still, its momentum would be exactly zero. That would mean its position could be infinitely precise, violating the rule. The universe does not allow such perfection. There is always a faint blur, a minimum level of activity. Now extend this reasoning to energy and time. Heisenberg's principle has a version that says the more precisely you know the energy of a system, the less precisely you can pin down when it has that energy. And conversely, the shorter the time interval you examine, the less well defined the energy is. Over tiny slices of time, energy can fluctuate, borrowed as if on loan, provided it is repaid quickly. It is this loophole that allows particles to appear from the vacuum, as long as they vanish again before the universe notices the debt. The vacuum becomes a playground for brief violations that are legal only because they are fleeting. This is why physicists sometimes speak of the vacuum as seething or foamy. The uncertainty principle guarantees that fluctuations can never be eliminated. No matter how hard you try to strip space bare, no matter how much you imagine removing every atom, every photon, every speck of matter, the uncertainty principle sneaks in. It whispers that position and momentum, energy and time can never both be locked down, and that whisper is enough to keep the vacuum buzzing with ghostly activity. It is easy to misunderstand this. Some imagine uncertainty as a statement about human ignorance, as if the particle really has a definite position and momentum, but we simply lack the skill to measure both. But that interpretation misses the point. The principle is not about us. It is about nature itself. The fuzziness is not in our tools, but in reality's fabric. The universe itself is indeterminate at its roots. That is what gives the vacuum its restless life. To grasp the scale of this, think of a simple analogy. Imagine you're trying to take a still photograph of a hummingbird's wings. If you use a very fast shutter speed, you capture a sharp image of where the wings are at one instant, but you lose information about their motion. If you use a longer exposure, you see the blur of motion, but you lose the precise position at any moment. At the quantum level, the universe always uses both settings at once. The world is not a collection of frozen snapshots, but a blur of possibilities. This strangeness has real consequences. In atomic physics, it explains why electrons do not simply collapse into the nucleus. Classically, you might expect negatively charged electrons to spiral inward toward the positively charged protons, radiating energy as they fall until atoms flatten into nothing. But uncertainty saves them. To confine an electron too tightly near the nucleus would make its momentum wildly uncertain, kicking it outward again. The fuzziness stabilizes matter. Without it, atoms and everything built from them would not exist. The uncertainty principle, unsettling though it sounds, is the reason the universe has structure at all. It also helps explain why no system can be perfectly still. Zero-point energy means that even the ground state of a field, its lowest energy configuration, is never zero. The vacuum seethes because uncertainty demands it, and once physicists realized this, they began to see how the vacuum might hold more than just fleeting particles. It might store enormous energy in its fluctuations, a possibility that continues to haunt cosmology today. What is so striking is that a principle expressed in simple terms, that you cannot know two properties with infinite precision at once, blossoms into such far-reaching consequences, from the stability of atoms to the evaporation of black holes, from the flickering of virtual particles to the expansion of the universe. Uncertainty lies beneath it all. It is not just a technical rule in textbooks. It is the trick the universe plays to keep nothing from ever being truly nothing. When Heisenberg first proposed his principle, many resisted. Even Einstein bristled, declaring that God does not play dice. The idea that reality itself was probabilistic, that certainty could never be restored, seemed intolerable. But decades of experiments confirmed it. Electron diffraction, atomic spectra, quantum tunneling, all aligned with Heisenberg's insight. The trick was real, however unsettling it seemed, and here lies a quiet irony. What once looked like a limit, a barrier to knowledge, turned out to be the key to creation. Because position and momentum cannot both be sharp, particles jitter. Because energy and time cannot both be sharp, fluctuations erupt. What seemed like uncertainty gave rise to possibility. The universe learned to conjure something from nothing, because it could never be perfectly precise. If you pause and think about it, there is something almost familiar in this. In our own lives, perfect clarity is rare. Our thoughts wander, our memories blur, our emotions shift. We cannot pin ourselves down completely, and yet out of that very uncertainty comes creativity. Ideas arise, solutions appear, moments of beauty unfold, not because everything was fixed, but because it was not. The vacuum's trick in that sense is not alien at all. It echoes the truth that possibility hides in uncertainty. As we drift further into this journey, remember that the Heisenberg uncertainty principle is not just a rule scribbled in notebooks. It is the heartbeat of the quantum vacuum. It ensures that emptiness is never empty, that silence is never silent, that the universe can shimmer with particles that were not there a moment ago. The trick is not a flaw. It is the foundation of the world we know. When we first spoke of the vacuum, it seemed like a place of absence, a background stripped of substance. Then it became a fabric, bending and stretching under Einstein's vision. Then it became restless, its quiet disturbed by Heisenberg's trick, flickering with particles that appeared and dissolved again. Now we arrive at a realization even more startling. Those flickers, those restless movements, are not just curiosities. They add up. And the result is something that sounds paradoxical, yet has become central to modern physics. The vacuum itself contains energy. It may seem strange to imagine emptiness as storing energy. In daily life, we think of energy as something you can point to. The warmth of a fire, the hum of electricity, the calories in a meal. If something is empty, it feels drained, without fuel. But the quantum world does not follow that intuition. Because uncertainty forbids perfect stillness, every quantum field retains a minimum amount of activity, even in its lowest possible state. This lowest state is called the vacuum state, but it is not truly empty. It is filled with zero-point energy. The vacuum, in other words, is not nothing but a sea of energy hidden beneath what we see. The idea first emerged in the early days of quantum mechanics, when physicists solved equations for oscillators, systems that move back and forth like a spring or a vibrating string. They discovered that the lowest energy was not zero but a small residual value. It was as if nature refused to let the pendulum hang perfectly still. Even at rest it trembled faintly. Extend this to every field that fills space: the electromagnetic field, the electron field, the Higgs field, and the conclusion follows. Every point in space hums with energy that cannot be removed. To visualize it, imagine the ocean on a perfectly calm day. At first glance, the surface seems still, a smooth mirror. But look more closely, and you see ripples, tiny movements that never cease. Even in apparent stillness, the sea is alive. The vacuum is like that ocean, not a barren void, but a surface stirred by invisible waves. The fluctuations may be too fine to see directly, but their presence is unavoidable. This energy is not just a theoretical curiosity, it leaves fingerprints in the real world. One example lies in the Lamb shift, a tiny change in the energy levels of electrons in hydrogen atoms. When physicists measured these levels with great precision in the mid-20th century, they found a slight discrepancy with predictions that ignored the vacuum. The solution was to recognize that electrons are not orbiting alone. They are surrounded by a cloud of virtual particles flickering from the vacuum. This subtle interaction shifts their behavior, and the measurements agree perfectly once vacuum energy is included. Another demonstration comes from the Casimir effect, which we visited earlier. Two metal plates, placed extremely close together in a vacuum, feel a force drawing them together. No particles, no air, no light exists between them, and yet the force is real and measurable. It arises because the quantum fields around the plates are restricted. Only certain modes of fluctuation fit between the plates, while others are excluded. Outside, all modes exist. The imbalance creates pressure. What appears to be empty space presses on matter with the weight of the quantum sea. The implications of this are staggering. If the vacuum holds energy everywhere, then the total across the universe must be immense. Calculations from quantum field theory suggest truly colossal values, energy densities so huge they defy comprehension. If correct, the universe would have curled in on itself long ago. But it has not. Something is missing. Some cancellation or balancing we do not yet understand. This mismatch between theory and observation is called the cosmological constant problem, and it remains one of the greatest puzzles in physics. Einstein encountered an early version of this when he inserted a cosmological constant into his equations of general relativity, trying to balance the universe into a static state. Later, when cosmic expansion was discovered, he regretted the move. But modern cosmology has returned to it, recognizing that vacuum energy might be the driver of accelerated expansion. What Einstein considered a blunder may in fact be essential. The quantum sea beneath the void could be pushing the cosmos apart, faster and faster, as galaxies drift like islands carried by a swelling tide. This possibility became unavoidable in the late 1990s, when two independent teams of astronomers measured the light from distant supernovae. They expected to see signs of slowing, as gravity tugged galaxies back together. Instead, they found acceleration. The expansion of the universe was speeding up. Something unseen, filling all of space, was driving it. They called it dark energy, but many suspect it is connected to the energy of the vacuum itself. If so, then the quiet hum of quantum fields shapes the fate of the cosmos. It is a humbling idea. What we think of as nothing, the very emptiness between galaxies, holds enough energy to determine the universe's destiny. The stars we see, the planets we know, the atoms we're made of, may all be secondary to the restless sea beneath. The quantum vacuum, once dismissed as mere nothingness, could be the most important something in existence. And yet, despite this, mysteries remain. Why does the energy we observe match neither the immense predictions of theory nor the neat cancellations physicists hoped for? Why is it small enough to allow galaxies and stars to form but large enough to accelerate expansion? It seems tuned with delicate precision, as though the universe balances on a razor's edge. Some propose deeper principles, hidden symmetries, or multiverse scenarios to explain it. Others accept it as a fact we do not yet understand. For now, the quantum sea continues to puzzle and inspire. In reflecting on this, it helps to return to human scales. Think of sitting beside the ocean. At times it feels calm, quiet, endless. But the longer you sit, the more you notice. The subtle sway of the tide, the almost imperceptible rise and fall of the horizon, the distant roar of waves. The vacuum's energy is like that hidden rhythm, an ever-present background that shapes everything even when we do not notice. It is the heartbeat of the cosmos, faint but decisive. Technologies too feel its touch. Quantum electrodynamics, the most accurate theory in science, rests on vacuum fluctuations. Without acknowledging the quantum sea, predictions would fail. Particle accelerators, lasers, atomic clocks all rely on the subtle corrections vacuum energy provides. The sea is not only cosmic but intimate, shaping the tools we use, the signals that carry information, the devices through which you hear these words now. This perspective shifts how we think about emptiness. No longer absence, it becomes potential. No longer hollow, it becomes foundational. The vacuum is not where things are missing, but where everything begins. The stars burn, the galaxies spin, the universe expands, all within the ocean of the quantum sea. And as we continue onward, deeper into this strange landscape, we will see how this sea is not only a stage for particles, but a source of them. Not only a presence in physics, but a mystery that ties together the smallest scales and the largest. The vacuum energy is both the whisper beneath atoms and the hand that stretches galaxies apart. Nothing has become everything, and everything rests upon the sea of nothing. By now we have grown used to the idea that emptiness is not empty. The vacuum hums with fluctuations, seethes with possibilities, and carries energy that may guide the fate of the entire universe. But ideas this strange are not easy to accept without something concrete, something you can point to and say, there it is. The Casimir effect is one of those rare bridges between theory and touchable reality. It is an experiment where the invisible restlessness of the vacuum presses on ordinary matter, where what we call nothing leaves fingerprints we can measure. The story begins in 1948 with a Dutch physicist named Hendrik Casimir. He worked at the Philips Research Laboratories, a place where theory met technology. Casimir was no stranger to the quirks of quantum mechanics. By then, physicists knew that fields filled space, and that even their lowest states carried energy. But how could anyone prove it? The vacuum seemed, by definition, beyond reach. Then Casimir had an idea, one deceptively simple, but profound. Imagine placing two metal plates extremely close together, parallel and uncharged, in what you would consider empty space. Remove all air, pump out every molecule, shut out every photon of external light. Between the plates there should be nothing, only vacuum. According to classical intuition, the plates should feel no force. They are neutral, with no electric or magnetic attraction. Yet Casimir predicted they would be drawn together, not by hidden charges, not by gravity, but by the vacuum itself. The reasoning is subtle but elegant. In the quantum view, electromagnetic fields fluctuate constantly, filling space with virtual photons that appear and vanish. These fluctuations are like waves of every possible wavelength rippling through emptiness. But between two closely spaced plates, only waves that fit neatly between them can exist. Longer wavelengths are excluded. Outside the plates, however, all fluctuations remain free. The imbalance means there is slightly less pressure inside than outside. The plates feel a gentle nudge pushing them together. It is as though the vacuum outside is fuller than the vacuum inside. What we call nothing has texture, and the plates reveal it by moving closer. At first, the prediction sounded almost fanciful. The effect was tiny, requiring separations on the order of micrometers, smaller than the width of a human hair. But physicists are persistent. Decades later, with careful instrumentation, the Casimir force was measured. Experiments confirmed that the plates did indeed attract, exactly as Casimir had predicted. The void, stripped of matter, reached out and touched the plates. The first clear measurements came in the late 1990s. Researchers suspended a small sphere close to a flat plate, avoiding the difficulty of aligning two plates perfectly. With precise control, they measured the attraction and found it matched the predictions of quantum field theory. Since then, the Casimir effect has been verified many times, using different shapes and setups, even with remarkable precision. What began as a theoretical curiosity became a tangible fact. The implications ripple outward. The Casimir effect is not just a laboratory trick. It shows that the vacuum exerts measurable forces, that quantum fluctuations are not metaphors but realities. It means that nothing can push, that absence itself has weight. And this weight, though small in the lab, might be enormous in the cosmos, shaping galaxies, steering expansion, defining destiny. To bring it closer to everyday life, think of two ships at sea, drifting close in calm water. Even without wind or engines, they may slowly move toward one another. The explanation lies in the waves. Outside the gap between the ships, waves of many sizes crash and roll. Inside, only small ripples can squeeze through. The imbalance nudges the ships together. The Casimir effect is similar, except the waves are not water but fluctuations of the electromagnetic field, and the sea is not liquid but vacuum itself. What makes the effect so haunting is that it forces us to reconsider the meaning of emptiness. For centuries, the void was seen as nothingness, an absence. Then it became a stage, then a fabric, then a restless sea. With the Casimir effect, it became a pressure you can measure, a force you can feel. The plates are like fingertips brushing the vacuum and discovering resistance where none should exist. This phenomenon also carries practical significance. At the scale of nanotechnology, where devices are built with components only a few atoms wide, Casimir forces matter. Tiny parts can stick together under its influence, altering how machines behave. Engineers designing micro-electromechanical systems, little gears, switches, and levers etched onto chips, must account for the vacuum's invisible pull. The Casimir effect is not just a cosmic curiosity. It is a factor in the technology inside your pocket. And yet, beyond these applications, the Casimir effect remains a profound philosophical marker. It is one of those moments where human beings, with fragile hands and clever tools, reached out into the void and discovered it was not void at all. It tells us that emptiness has structure, that silence hums, that the very act of stripping away reveals hidden fullness. Physicists have since explored variations. What happens if the plates are not perfect conductors but different materials? What if the gap contains some medium rather than perfect vacuum? What if the geometry changes? Each variation alters the balance of fluctuations, producing repulsion in some cases instead of attraction. The vacuum, it turns out, can be sculpted. Its pressures and whispers shift depending on boundaries and shapes. Nothingness can be engineered. This realization has sparked dreams of harnessing vacuum forces in novel ways. Some speculate about futuristic propulsion, others about energy extraction, though such hopes remain distant. What matters most is the principle. The vacuum responds to matter, and matter responds in return. It is an interaction, not a backdrop. It also links back to the great puzzles of cosmology. If the Casimir effect demonstrates vacuum energy in the lab, why do our calculations for the universe's vacuum energy differ so dramatically from observation? Why does the small force nudging plates in a laboratory not swell into an overwhelming force in the cosmos? The same vacuum reveals itself at different scales and contradictory ways, leaving us humbled and puzzled. If you let your mind wander, you can imagine the plates as metaphors. Two silent presences, facing one another across an empty gap, slowly drawn together by a force no eye can see. Their attraction is not love or gravity or magnetism, but the whisper of nothingness, the pressure of the void. It is a reminder that even in apparent emptiness, unseen currents flow, shaping connections, pulling things closer. As the night deepens and your breathing slows, the Casimir effect offers a kind of quiet comfort. It tells us that what feels empty is never truly barren, that the silence around us, the spaces we think of as gaps, are filled with subtle presence. That nothingness, paradoxically, carries weight. And as we drift onward, we carry this lesson with us. The vacuum is not absence, but fullness disguised. Two plates resting in stillness reveal a truth about the cosmos itself. Emptiness presses back. Nothing is never nothing. The closer we look at the vacuum, the less it resembles the simple emptiness that words like nothing suggest. The Casimir effect already showed us that invisible forces emerge where we least expect them. Now we go deeper into the very flickers that give the vacuum its restless energy. Here we find the strange creatures of quantum mechanics, virtual particles, phantoms that live for a heartbeat, borrowing existence from the uncertainty principle before fading again. They are not the stable, enduring particles that make up matter and light. They are temporary guests living on borrowed time. It may sound almost mystical, particles that come from nowhere and vanish back into nowhere. But in physics, the idea is precise. Virtual particles are not objects you could scoop into a container or photograph with a camera. They are terms in the calculations of quantum field theory, ripples in the equations that describe how fields interact. Yet even though they cannot be isolated, their presence alters reality in ways that can be measured. To understand this, recall the principle we explored before. The more precisely you try to pin down a system's energy, the less precisely you can pin down when that energy exists. The shorter the time you look, the less strict the rules of energy conservation become. For fleeting instants, energy can be borrowed, like a loan from nature's bank, provided it is paid back before the books are checked. From this allowance arise pairs of particles and antiparticles, springing into being and then annihilating each other before they can be caught. These are the virtual particles, existing in the gaps permitted by uncertainty. Think of it like ripples in a crowd at a stadium. From a distance you see the wave travel around, people raising their arms in sequence. No one person moves far, but the ripple looks real. Virtual particles are similar. They are not permanent entities, but disturbances in fields, momentary ripples that nevertheless have effects. Those effects are everywhere. Take, for instance, the force between two electrons. Classically, we might think of it as a simple electric repulsion, two like charges pushing one another apart. But in the language of quantum field theory, this force arises because virtual photons, particles of light, are exchanged between them. The photons are not real, detectable light. They exist only during the interaction, borrowed briefly from the vacuum to carry the message of repulsion. Without them, the force would have no medium. The same is true for the strong nuclear force that binds protons and neutrons inside the nucleus. Virtual particles called gluons mediate that force, exchange constantly to hold the nucleus together against the mutual repulsion of protons. Without these ephemeral messengers, matter itself would disintegrate. The vacuum's borrowed existences are the glue of the world. Other phenomena bear their signature as well. The Lamb shift in hydrogen, which puzzled physicists until they accounted for the effect of virtual particles surrounding the electron. The magnetic moment of the electron, measured to astonishing precision, requires the contribution of countless virtual particles flickering in and out. Each slight correction builds until the theory and experiment align almost perfectly, better than any other agreement in science. It is because of these ghosts that the predictions work. Perhaps the most dramatic example lies at the edge of black holes. As we touched on earlier, when a virtual particle pair appears near the event horizon, one can fall in while the other escapes. Ordinarily they would annihilate, vanishing back into nothing. But separated, one becomes real, carrying energy away. This is Hawking radiation, and it means black holes are not eternal, but slowly evaporate. The most permanent structures in the cosmos are undone by the fleeting whispers of virtual particles. If you pause to think about it, there is something unsettling about this. We like to think of the world as solid, built from enduring things. But much of its structure depends on entities that exist only briefly, never to be observed directly, never to be captured. This stable world rests on unstable foundations, the permanent on the temporary. It is as if reality leans on shadows, and yet those shadows hold. Of course, not all physicists are comfortable speaking of virtual particles as if they were little objects. Some insist they are just mathematical artifacts, ways of keeping track of terms in equations. And that is true, in a sense. But equations shape reality, and when the results match experiments to 1 part in a trillion, it is hard not to feel that these ephemeral players deserve recognition as part of the world, however strange. We can also find analogies closer to human experience. Think about how many ideas cross your mind in a single day. Most of them flicker and vanish, unformed, unspoken, forgotten. Yet some of those fleeting thoughts leave ripples. They guide your mood, spark creativity, alter decisions. Even what never fully becomes something can still change everything. Virtual particles are like that. Brief presences, half real, yet powerful. There is also an echo here of the way societies work. Most of history is not the grand events, but the tiny interactions, the countless exchanges between people that never make records. A glance, a brief word, a forgotten kindness or cruelty, moments that seem to vanish yet shape the flow of lives. Virtual particles are the hidden interactions of the universe, the exchanges that do not endure but without which nothing would be the same. At the technical level, their existence forces physicists to invent tools to handle infinities. In quantum field theory, the contributions of virtual particles can pile up endlessly, threatening to swamp calculations. Physicists developed renormalization, a method of taming these infinities, subtracting what is unphysical and keeping what is real. To outsiders, it can look like mathematical trickery. To physicists, it is a testament to how deeply virtual particles pervade reality. Without them, the theory fails. With them, it becomes the most successful description we have of the natural world. All of this suggests that the line between real and virtual is not as clear as we imagine. What is real? The stable particle we can detect that endures long enough to measure. What is virtual? The brief fluctuation, the messenger that never quite materializes, but both shape reality, both matter. And sometimes, as with Hawking radiation, what begins virtual can become real. This is perhaps the deepest lesson. The vacuum does not merely sit idle, occasionally rippling. It is an engine of creation, producing entities that are almost real, sustaining interactions that would otherwise fail, and even, under the right conditions, giving birth to particles that escape into the world. Borrowed existence is not wasted. It is the foundation on which lasting existence rests. and as you drift with this thought, you may notice how it softens even our own sense of impermanence. So much of life feels fleeting, so many moments seem to vanish. But perhaps what is brief is not meaningless. Perhaps what flickers for a moment leaves traces that endure, shaping outcomes we never see. The universe itself works this way. Its most stable structures depend on what was never fully real. The borrowed becomes the basis of the lasting. So the next time you think of nothingness, remember the crowd of shadows that fill it. They do not last, they cannot be bottled, but they change everything. They are the whispers of the quantum sea, the ghosts of the vacuum, the virtual particles whose borrowed existence holds up the real. All along our journey, the vacuum has grown stranger with every step. At first, it seemed to be emptiness, then a stage, then a restless sea alive with flickers and whispers. We have seen how virtual particles borrow existence, shaping events that endure long after they vanish. Now we come to an even deeper realization, one that rewrites how we understand the very idea of a force. What if every interaction, every push and pull, every attraction and repulsion arises from the vacuum? What if what we call forces are simply the language of the vacuum, the way its hidden energy and fluctuations communicate between particles? To most of us, the word force feels straightforward. It is what you feel when you push a door open, when you pull a drawer shut, when the ground resists your step, when gravity tugs on your body. Forces are the stuff of daily life, tangible and immediate. For centuries, scientists thought of them that way too, as direct actions, one thing imposed on another. Newton's gravity was an invisible hand pulling planets toward the sun, his laws of motion describing how bodies respond to pushes and pulls. But as physics evolved, this picture began to dissolve. With the rise of field theory, forces were no longer direct pulls at a distance. Instead, objects influenced the space around them, and other objects responded to that field. A charged particle altered the electromagnetic field, and another charged particle felt the change. Gravity bent the fabric of space-time, and other masses followed the curves. Already the vacuum had begun to step out from the shadows, for fields are not things laid on top of space. They are inseparable from it. Quantum mechanics deepened the transformation. Forces became not just fields, but the exchange of virtual particles. The electromagnetic force, the strong nuclear force, the weak nuclear force, all could be described as particles borrowing existence to shuttle momentum back and forth. Even gravity in some approaches is imagined as carried by hypothetical particles called gravitons. The vacuum itself supplies the messengers, and the messengers create what we call force. Consider the electromagnetic force again, perhaps the most familiar. When two electrons repel each other, it is not because they sense one another directly, nor because they send beams of light across the gap. It is because the vacuum between them allows the exchange of virtual photons, ripples of the electromagnetic field that flicker just long enough to transfer information. The repulsion you would measure is, in truth, the whisper of the vacuum arranging its fluctuations. The strong nuclear force is stranger still. It binds quarks inside protons and neutrons, and binds those protons and neutrons into nuclei. The messengers here are gluons, particles that themselves carry the very charge they transmit. The vacuum swarms with gluonic activity, so dense that individual quarks can never be isolated. They are confined forever, bound in trios, because the vacuum does not permit otherwise. In this way, the vacuum is not just the medium, but the enforcer of the strong force, shaping matter at its root. The weak nuclear force, responsible for radioactive decay and for processes that fuel the sun, works through heavy virtual particles called W and Z bosons. Their fleeting exchanges allow transformations that seem improbable. Neutrons becoming protons, neutrinos slipping through matter as though it were smoke. Once again, the vacuum provides the means, the short-lived intermediaries that make the impossible possible. Even gravity, that most ancient and familiar of forces, is suspected to arise from the vacuum structure. In Einstein's view, mass and energy curve space-time and motion follows those curves. But some physicists dream of describing gravity as another quantum force, its interactions mediated by virtual gravitons. Whether or not this view is correct, the implication remains. What we call the force of falling apples or orbiting planets is the manifestation of the vacuum's geometry and its restless exchange. The realization that the vacuum is the source of forces reframes everything. No longer is the void a backdrop where forces act. The void is the actor. The vacuum is not the stage, but the play itself, speaking through fluctuations, shaping trajectories, binding matter. The pushes and pulls of the universe are the grammar of nothingness. It is tempting to think of this in terms of communication. Imagine two friends seated across a quiet table, passing notes back and forth. They do not touch directly, but each learns what the other is thinking through the notes. The vacuum is the table, and the notes are the virtual particles, carrying messages that manifest as attraction or repulsion. To an outsider, it looks as if the friends simply lean closer or further apart. But in truth, it is the unseen exchange that makes it happen. Another image might be the way sound travels. If you tap the surface of a drum, vibrations ripple through the air and reach another ear. The air is not empty. It carries the disturbance, the wave, the signal. Forces work the same way, except the medium is not air but the quantum vacuum itself. Every push and pull you feel is the echo of ripples in nothingness. This changes how we see permanence. The atoms of your body do not hold together because of some intrinsic glue, but because the vacuum permits exchanges that bind electrons to nuclei to one another, and quarks inside protons. You are held together by borrowed existences, by messages passed across the void. What you call your solidity is, at root, the restless whisper of emptiness. And yet this whisper is extraordinarily reliable. The laws governing the vacuum's exchanges are precise, repeatable, testable to astonishing accuracy. The electron's magnetic moment has been measured and calculated to more than 10 decimal places, and they match. The stability of matter, the chemistry of life, the burning of stars, all depend on the vacuum's consistency. The most fleeting interactions create the most enduring world. This perspective also reveals why the vacuum is so central to modern physics. When physicists attempt to unify forces to describe electromagnetism, the weak force, the strong force, and perhaps gravity in a single framework, they are trying to understand the structure of the vacuum. Grand unification is not just about particles. It is about the underlying sea that makes particles possible. Even beyond unification, the vacuum sets the stage for symmetry breaking, for the Higgs field that gives particles their mass. Without the Higgs vacuum, the universe would be a soup of massless entities rushing at the speed of light, incapable of forming atoms. With it, particles acquire weight, structure emerges, stars ignite. Once again, the vacuum is not passive. It dictates what can exist and how. What we call forces, then, are the vacuum's way of ensuring that matter and energy communicate, that they do not drift in silence but interact. They are not external rules imposed from outside the universe, but consequences of the universe's own fabric. And this fabric, restless and uncertain, ensures that nothing can ever be nothing, that absence always holds presence, that stillness is always alive. Think of how this echoes in your own life. The strongest connections between people are often invisible, unseen forces of trust, care, memory. They are not objects you can hold, yet they shape everything. The vacuum's forces are like that. You cannot scoop up a gluon, or pin down a virtual photon or touch a graviton, but without them the universe would fall apart. The unseen holds the seen. The hidden carries the weight of the world. And so, when you feel the pull of gravity, when you see magnets cling, when you know that atoms endure, remember that these forces are not imposed from above. They are the hum of the vacuum, the dance of virtual messengers, the inevitable result of uncertainty and fluctuation. The vacuum is not the absence of reality. It is reality's source, its author, its voice. The universe you inhabit is not built atop a hollow foundation. It is woven from whispers, stitched by unseen exchanges, bound by the vacuum itself. What feels like force is nothing more than nothing, speaking in the only language it knows. If the vacuum can whisper forces into being, if it can press on plates and bind matter together through invisible messengers, then perhaps it should not surprise us that it also has the power to shape the very largest scales of existence. The idea that the vacuum is alive with energy does not end with particles or atoms. It extends outward into the earliest history of the cosmos, into an era so brief and yet so decisive that it determined everything that followed. This is the story of inflation, a time when the energy of nothing itself may have blown the universe into being. To imagine inflation, picture the universe just after its birth. Cosmologists speak of the Big Bang, but the phrase can be misleading. It was not an explosion in space, like fireworks bursting outward. It was the expansion of space itself. In its first instant, the universe was unimaginably small, hot, and dense, packed with energy far beyond anything we can reproduce. And then something extraordinary happened. In a fraction of a second, the universe swelled exponentially, doubling and doubling again, faster than the blink of an eye. This brief phase of runaway expansion is what physicists call inflation. Why do they believe it happened? Because when we look at the universe today, we find clues that demand an explanation. The cosmos is astonishingly uniform. Galaxies scattered billions of light years apart shine against a background radiation that is almost the same everywhere, differing only by tiny ripples. If the universe had expanded at a steady pace from the beginning, there would not have been time for such distant regions to exchange information, to smooth themselves out. They would be forever strangers, and yet they are alike, as if some hidden hand ironed out the wrinkles. Inflation provides that hand. In its furious expansion, regions once close together were stretched apart, imprinting uniformity across the sky. There is also the problem of flatness. Measurements show that the universe is very nearly flat, meaning its geometry is not curved like a sphere nor saddle-shaped, but balanced between the two. That balance is precarious. Without inflation, it would be almost impossible for the universe to begin so finely tuned. But rapid expansion dilutes any initial curvature, flattening space like stretching a balloon until its surface feels flat beneath your feet. Inflation explains the balance. And then there is the mystery of relics. Early theories predicted the Big Bang should have created exotic heavy particles in abundance, remnants that could still linger today, yet we do not see them. Inflation solves this too, stretching space so dramatically that any such relics were dispersed into near nothingness. The problems vanish under expansion, but what could drive such a process? What could cause space to expand so violently and then stop? Here the vacuum takes the stage again. Physicists propose that inflation was powered by a field filling all of space, something like a cousin to the Higgs field, whose potential energy acted like a cosmological constant for a brief moment. The field's vacuum energy dominated, pushing space apart at extraordinary speed. When the field decayed into particles and radiation, inflation ended, leaving behind the hot soup of the young universe. In this picture, the energy of nothing is not a passive background, but the very engine of creation. What looks to us like emptiness contained enough power to sculpt the cosmos. The galaxies, the stars, the atoms, all trace their origins to a fleeting moment when vacuum energy surged. Inflation is the echo of nothingness reshaping everything. This idea also ties back to quantum fluctuations. During inflation, the vacuum's restless flickers were stretched to cosmic scales. Tiny ripples in energy density became the seeds of galaxies, amplified by expansion into structures that billions of years later condensed into stars and planets. every cluster of galaxies in the night sky, every swirl of cosmic web may trace back to a quantum fluctuation, a borrowed existence magnified into permanence. In that sense, we live in a universe built from the vacuum's whispers, from accidents of uncertainty frozen into matter. It is an unsettling but also beautiful vision. The vastness of the sky, the shining sweep of the Milky Way, the galaxies spiraling in their billions, all of it might be the fossilized trace of quantum jitters in the earliest vacuum. The randomness of nothing became the architecture of everything. Inflation also invites us to think of beginnings differently. Instead of the universe leaping into being fully formed, it may have emerged through phases shaped by the properties of fields and vacua. What we see as stable laws today may be the outcome of transitions, of the vacuum settling into its present state. Physicists sometimes speak of false vacua, states that seem stable but are not, and of true vacua, deeper and more enduring. Inflation could have been the universe rolling from one vacuum to another, the energy released in the fall driving expansion. Nothing changed state, and in the process, everything began. This leads to speculations that stretch imagination even further. If inflation is driven by vacuum states, could it happen more than once? Could it still be happening elsewhere? Some theories propose eternal inflation, where different regions of the cosmos fall into different vacua, creating bubble universes beyond our horizon. Each bubble may have its own laws, its own particles, its own story. Our universe, in this view, is one bubble in an endless froth, each born from the energy of nothing. For now, these remain speculations. What matters most is that inflation explains what we see: the smoothness, the flatness, the lack of relics, the seeds of galaxies. It is a theory born from necessity, but it has grown into one of the most compelling stories science tells, and at its heart lies the same theme we have followed all along. Nothing is never truly nothing. The vacuum is restless, potent, generative. Its energy can push plates together in a lab, and it can drive the birth of universes in the cosmos. The scale is almost impossible to comprehend. In less than a trillionth of a second, the universe expanded by a factor greater than we can fathom, turning something microscopic into a cosmos billions of light years wide. And yet this unimaginable transformation was powered not by matter, not by fire, but by vacuum energy, by the latent potential of emptiness. The quietest of all realities proved the most explosive. To bring this closer to home, think of breathing. At rest, a breath feels like nothing, almost unnoticeable. And yet that gentle rhythm sustains everything, carries life through quiet repetition. Inflation was like a single breath of the universe, except in that breath, emptiness expanded into all we know. The galaxies above, the stars across the night, the atoms within your body, all are the children of nothing, shaped by a moment when the vacuum exhaled. Inflation is not just a theory of physics. It is a reminder that absence holds potential, that what looks like nothing can be the most powerful force of all. For most of human history, the night sky looked still. The stars traced slow paths over hours, the planets wandered patiently across months, but the heavens themselves seemed eternal and unchanging. Then came the 20th century, and with it, discoveries that overturned the old sense of stillness. Astronomers peered deeper, gathered light from distant galaxies, and saw something astonishing. The universe was not fixed at all. It was expanding. Galaxies were drifting away, the farther ones faster, as though space itself were stretching. This was already strange enough, but late in the century another surprise arrived, one even stranger. Not only was the universe expanding, it was accelerating. Space was stretching faster and faster, driven by a mysterious agent that astronomers now call dark energy. Dark energy is not like the matter we know, nor like the radiation that shines. It does not clump into galaxies or stars. It does not glow, scatter, or collide. Instead, it works invisibly, woven into the fabric of space itself, gently but relentlessly pushing the cosmos apart. Its discovery came as a shock. In the 1990s, 2 teams of astronomers set out to measure the expansion rate of the universe by observing distant supernovae, stellar explosions so bright they can outshine whole galaxies. These supernovae act like cosmic mile markers, their light telling us how far away they are and how fast the universe has been expanding at different times. The expectation was simple. Gravity pulls things together, so over time the expansion of the universe should have been slowing down, like a ball thrown upward gradually losing speed. But the data told a different story. The supernovae were dimmer than expected, meaning they were farther away than they should have been if expansion had been slowing. The only explanation was that the expansion had sped up. The universe was accelerating, as though some hidden energy were overpowering gravity. What could this energy be? The simplest idea is that it's the energy of the vacuum itself, a cosmological constant built into the fabric of space. If the vacuum has energy, it acts like a pressure that does not thin as the universe expands. Matter and radiation dilute as space stretches, their density dropping. But vacuum energy remains constant, the same per volume of space. As space grows, there is more vacuum, and so more energy. The result is a force that pushes outward, ever stronger as the cosmos grows larger. In this picture, dark energy is nothing more than the vacuum's silent hum, the same restlessness we have seen in the Casimir effect, in virtual particles, in inflation. The difference is scale. On the smallest scales, it nudges plates together. On cosmic scales, it drives galaxies apart. The vacuum shows itself everywhere, from the lab bench to the stars. The mystery, though, is magnitude. Theoretical calculations of vacuum energy predict a value far, far larger than what observations reveal. If the equations are taken literally, the universe should have torn itself apart instantly, inflated beyond recognition. Instead, the measured value of dark energy is tiny but not zero. It is enough to accelerate expansion, but not enough to overwhelm matter and radiation. This mismatch is sometimes called the worst prediction in physics, a discrepancy of more than 100 orders of magnitude. It is as though you calculated the height of a tree and predicted it would stretch past the moon, only to find it barely reaches your window. Physicists puzzle over this. Perhaps our methods of calculation are flawed, or perhaps some deeper principle cancels most of the vacuum energy, leaving only a trace. Or perhaps dark energy is not a simple constant at all, but something more dynamic, a field evolving over time. They call such possibilities quintessence, imagining a new kind of energy that changes as the universe ages. For now, the evidence is not clear enough to decide. What we do know is that dark energy dominates the universe today, making up about 70% of its total content. Matter, stars, gas, galaxies, even the dark matter that binds them, accounts for less than a third. Radiation, once dominant, is now negligible. The vacuum rules the cosmos. This raises profound questions. If dark energy continues its work, what will the universe's fate be? One possibility is the Big Freeze. Expansion will accelerate forever, galaxies drifting apart until their light no longer reaches one another, stars burning out, black holes evaporating, leaving only a cold, dark, silent universe. Another, more extreme, is the Big Rip. If the acceleration grows without bound, even galaxies, stars, planets, and atoms could be torn apart by the stretching of space itself. There are other possibilities too, depending on whether dark energy is constant or variable, but all carry the same theme. The vacuum dictates the end as much as the beginning. To bring this closer to everyday thought, imagine a balloon. At first you blow gently, the rubber stretches slowly, then you blow harder, and it swells faster. Dark energy is like a pressure inside the balloon, except the balloon has no skin. no boundary. It is space itself that stretches, galaxies riding along like dots drawn on the surface. Unlike a balloon, there is no centre, no edge. Every point recedes from every other, driven apart by the invisible hand of dark energy. And yet, as strange as it is, dark energy fits seamlessly into the story we have been weaving. Nothing is never nothing. The vacuum is full, restless, alive. Its fluctuations create particles, its forces hold matter together, its energy inflated the universe, and now, in its quiet persistence, it accelerates the cosmos into the future. From the tiniest scale to the largest, the same theme emerges. Emptiness is the source of motion. Astronomers continue to study dark energy, mapping galaxies, measuring cosmic microwave background radiation, watching supernovae flicker in distant skies. Each new observation refines the story but also deepens the puzzle. The more we know, the more enigmatic the vacuum becomes. Is dark energy truly constant? Is it tied to fields we have yet to discover? Could it decay someday, changing the fate of everything? These are not questions with answers yet, but they guide the work of countless scientists staring into night skies and trying to hear the whisper of nothing. And as you listen now, perhaps in the quiet of your room, the idea of the universe expanding silently around you might feel abstract, remote, but in a way it is happening everywhere. Space itself is stretching, between galaxies, between clusters, even between us and the farthest horizons. Though on small scales it is overwhelmed by matter's gravity, on the larger scales it rules. We live not in a static stage but in a dynamic sea, carried outward by the energy of nothing. So the next time you look up and see the stars, remember that they are not fixed in place, but drifting away, slowly at first, then faster, propelled by a presence that seems like absence. Dark energy is not dramatic in daily life. It does not tug on your body or make planets spin differently. But it is the silent architect of the universe's future, the hidden rhythm to which galaxies dance. The vacuum, once thought to be empty, now writes the fate of all things. When you hear about dark energy stretching galaxies apart, when you picture cosmic inflation or black holes evaporating through the whispers of virtual particles, it can feel as though the vacuum is a story that belongs out there, at scales far removed from your own life. The stars above, the vastness of space, the beginning and the fate of the cosmos, these are the natural stages for nothingness to play its strange role. And yet, if you look inward instead of outward, you find the same story written in miniature. The vacuum is not only out in the galaxies, it is inside you, woven into your very body. Every atom that makes you is mostly empty space. This is not a metaphor but a straightforward truth of physics. Picture a simple atom, like hydrogen, the most common in the universe and abundant in your body as well. At its centre sits a proton, a tiny speck of matter. Orbiting around it is an electron even lighter and smaller, bound by the electromagnetic force. If you enlarge that atom until the proton were the size of a marble, the electron would be circling somewhere near the edge of a sports stadium, and between them, nothing but vacuum. This ratio holds for all atoms from carbon to oxygen to iron. The nuclei made of protons and neutrons are clustered like grains of sand at the core, while the electrons swirl in shells that stretch outward. The distances between them are vast compared to their sizes. If you could somehow remove the emptiness, if you could squeeze all the matter in your body so that the nuclei touched, you would be compressed to a speck smaller than a grain of rice. Almost everything that gives you shape is emptiness. You are, in a very real sense, made of vacuum, and yet this emptiness is not nothing. It is alive with activity, filled with quantum fields, with fluctuations that never rest. The reason your body feels solid when you press your hand against your arm, when you lean against a wall, is not because the atoms are packed tightly together like bricks. It is because the electrons in those atoms resist being forced into the same state. their fields interacting through the vacuum, creating the sensation of firmness. Solidity is a negotiation between emptinesses, a dialogue across space that is mostly void. This is one of the most counterintuitive things about existence. We imagine ourselves as solid beings moving through empty space. In truth, we are mostly empty space moving through more empty space, stabilized by forces that emerge from fluctuations in the vacuum. The weight you feel when you sit, the resistance you sense when you grip something, the very structure of your bones and muscles, all of it depends on emptiness doing the work. There is another layer still. The protons and neutrons in your body are not solid balls of matter, but themselves made of quarks, held together by gluons, the messengers of the strong nuclear force. And between those quarks, more vacuum, seething with activity. In fact, most of the mass of a proton does not come from the quarks themselves, which are feather-light, but from the energy of the gluons and the vacuum fluctuations inside. The weight of your body is quite literally the energy of nothing in motion. This realization can feel almost dizzying. When you touch your arm, you're touching emptiness held in place by emptiness. When you breathe, you draw in atoms that are mostly void. When your heart beats, it is pumping cells whose solidity is an illusion, created by interactions of fields across space that is fundamentally empty. And yet, from this emptiness arises life, thought, memory, and experience. It might help to picture it differently. Imagine a great cathedral, tall ceilings arching above, vast spaces stretching between columns. To the eye, the cathedral looks full of structure, solid stone shaping form and meaning. But most of what you see is empty air, spaces framed by stone. The stone is essential, but without the emptiness, the cathedral would not be what it is. Atoms are like that. Their particles are the columns, but the vacuum in between shapes the form, the behavior, the chemistry that gives rise to life. There is something humbling about realizing that most of what you are is emptiness. But there is also something reassuring. Emptiness does not mean absence. It means potential, activity, structure. The vacuum is not a void that subtracts, but a field that allows. It is what permits electrons to orbit, protons to bind, atoms to combine into molecules, molecules into cells, cells into organs, and organs into you. Without emptiness, nothing could exist. Think about water. The properties of H2O depend not just on the atoms themselves, but on the angles, the space between them, the emptiness through which they connect. That space determines whether water flows as a liquid, freezes into ice, or steams into vapor. The same is true for proteins, whose intricate folds determine the machinery of life. Those folds are defined by the space around atoms, by the emptiness within and between them. Life is not simply matter. It is matter shaped by the vacuum. And yet, it is easy to forget this. When you knock on a wooden desk, you hear the firmness of contact. When you stand on the ground, you feel stability beneath your feet. But that firmness is the result of electromagnetic forces playing out across space that is mostly void. At the deepest level, it is the vacuum interacting with itself. Even your thoughts depend on emptiness. Neurons fire, sending signals through your brain, and those signals are carried by ions moving through channels in cell membranes. But the atoms in those channels, the atoms in the neurotransmitters, are bound and structured by the same emptiness. If the vacuum were truly empty, none of it would work. The silence of the void is the source of the voice in your head. There is another perspective worth considering. The vacuum inside your body is not separate from the vacuum of the cosmos. It is the same. The space between electrons and nuclei is continuous with the space between stars. The nothingness that drives galaxies apart is the same nothingness that gives you shape. You are not merely in the universe, you are of it, stitched together by the same restless fabric that spans billions of light years. The energy of nothing courses through you, holds you, defines you. This is not to say you are insubstantial, quite the opposite. You are living proof that emptiness is not absence but presence of a deeper kind. The fact that atoms hold together, that molecules form, that cells thrive, shows that emptiness is fertile. Without the vacuum, you would not exist. The void within is not a lack, it is your foundation. And as you rest with this thought, notice how it changes the way you might feel about yourself. You're not fragile because you're mostly empty. You're resilient because emptiness allows flexibility, motion, interaction. The vacuum gives you the space to exist, to think, to grow. The universe is not built on nothing. It is built on a nothing that is everything. The next time you place your hand on your chest and feel your heartbeat, remember that what you are touching is a rhythm built on space. The pulse you feel is not just muscle and blood, but the dance of atoms across emptiness, the play of forces that emerge from the vacuum. You are, quite literally, the vacuum's way of becoming aware of itself. If most of what you are is emptiness, and if the stars themselves are guided by the same invisible sea, it may seem as though the vacuum is a purely philosophical idea, something to be pondered but never touched. And yet, one of the most remarkable things about modern science is that we can not only think about the vacuum but measure it, probe it, experiment with it, and feel its effects in controlled ways. The notion of nothing might sound intangible, but physicists have built machines that coax whispers out of the void and register them as unmistakable results. One of the most famous demonstrations of this is the Casimir effect, something we glimpsed before. In this experiment, two flat metal plates are placed extremely close together in a vacuum. Nothing, one might think, should happen between them. No air, no particles, just empty space. And yet, the plates feel a force nudging them toward one another. This is not magnetism, not static electricity, not a hidden current in the lab. It is the vacuum itself pressing them together. The explanation comes from quantum fluctuations. The plates restrict which virtual particles can appear between them. Outside, the vacuum fluctuates freely, but between the plates only certain modes are allowed. The imbalance creates a pressure, pushing the plates closer. Here, in a quiet laboratory, scientists see the fingerprints of nothing. Measuring this effect is delicate work. The force is tiny, almost unimaginably so, requiring extremely smooth plates, precise alignments, and sensitive detectors. But the measurements agree with predictions. The vacuum, once thought to be absence, exerts a real, measurable influence. What was once philosophy becomes physics, translated into numbers that can be written down and checked again and again. Another way we touch the vacuum is through particle accelerators. These vast machines, such as the Large Hadron Collider near Geneva, smash particles together at enormous energies. In the debris, new particles appear. Fleeting existence is born from the vacuum itself. According to Einstein's equation, energy can become mass. The accelerator's collisions provide the energy, and the vacuum responds by producing particles, some stable, some vanishing almost immediately. The discovery of the Higgs boson in 2012 was a triumph of this method. The Higgs field, an aspect of the vacuum itself, revealed its particle in the showers of debris, confirming that what seems like empty space is structured, giving mass to the particles that form matter. Even the simple fact that particles can appear and disappear in experiments is evidence of the vacuum's richness. When electron-positron pairs flicker into being and annihilate, detectors pick up the gamma rays they release. What looks like a fleeting blip of nothing has a signature, a trace we can measure. The vacuum's fluctuations, though brief, leave echoes that machines can hear. Astrophysics, too, offers experiments on the vacuum, though on scales no laboratory can match. Observations of the cosmic microwave background, the faint afterglow of the Big Bang, show tiny ripples imprinted by quantum fluctuations during inflation. The vacuum's restless energy, magnified by cosmic expansion, left marks still visible billions of years later. Satellites like WMAP and Planck have mapped these ripples with exquisite detail, confirming predictions and strengthening the case that the universe itself is an experiment in vacuum physics, a record of nothing made visible. Another frontier lies in attempts to detect vacuum birefringence, a subtle effect predicted by quantum electrodynamics. In strong magnetic fields, the vacuum should behave like a medium that affects light's polarization, as though empty space itself were a lens. Experiments with powerful lasers and magnetic fields are pushing toward detecting this. If confirmed, it would be yet another way the vacuum speaks, turning absence into measurable influence. There are even efforts to test whether the vacuum energy might change over time, probing whether dark energy is constant or dynamic. Telescopes scan the sky, charting the distances of galaxies, watching supernovae flare, seeking hints of evolution. If the vacuum shifts, it could alter the universe's fate. These observations are experiments written on the canvas of the cosmos, tests whose apparatus spans billions of light years. One of the most poetic experiments is the Unruh effect, though it remains beyond current reach. The theory predicts that an observer accelerating through the vacuum will perceive it not as empty, but as filled with a warm bath of particles, a kind of heat generated by motion itself. The faster you accelerate, the hotter it seems. This suggests that even the perception of nothing depends on how you move through it. Though we have not yet measured the Unruh effect directly, it stands as a reminder that the vacuum is not a fixed stage but a participant, its character shifting with perspective. Even in more practical terms, the vacuum shows itself. In semiconductors, the behavior of electrons depends on quantum fields, on fluctuations that are inseparable from the vacuum. In precision measurements, corrections from virtual particles must be included to match experimental data. Engineers may not speak of nothingness when designing electronics, but the devices in your pocket whisper the same story. Emptiness has structure. What makes all this extraordinary is the transition from the abstract to the tangible. The idea of nothing was once debated in ancient forums, argued over by philosophers who could only imagine. Now, in gleaming laboratories and orbiting satellites, we can measure the pull of the vacuum on plates, detect particles birthed from emptiness, trace fluctuations across the cosmos. The void has stepped down from the realm of speculation into the realm of experiment. To grasp how delicate these experiments are, think of the Casimir force again. It is smaller than the weight of a gnat's wing, and yet with careful instruments scientists detect it. Or think of the Higgs boson, a particle that appears for less than a sextillionth of a second, and yet its presence was confirmed by signatures amid mountains of data. These are not the blunt results of hammers and scales. They are the results of patience, precision, and a deep trust that even nothing will reveal itself if you look closely enough. And so, the laboratory becomes a place where absence is studied like substance, where scientists coax out the truth that the vacuum is alive. When you hear of these experiments, it might seem remote, something happening in clean rooms and caverns beneath the earth, but their implications reach into you, into every atom of your body, into every star you see. They are confirmations that the story of nothing is real, not only in equations but in measurements, in evidence, in results you can write down in ink. The emptiness you carry inside you, the emptiness between galaxies, the emptiness beneath magnets and wires, all of it is one. And when scientists touch it, they are not just measuring an effect. They are holding a mirror up to the universe, showing us what absence truly is. When experiments begin to confirm what was once only speculation, the story often circles back to philosophy. It is natural. Humans have wondered about nothing for thousands of years, long before anyone could measure the pressure between plates or detect particles in a collider. Now that physics has shown us the vacuum is not empty, the old question arises again, but in a sharper form. What truly is nothing? For the philosophers of antiquity, nothing was the hardest concept to hold in the mind. Something can be touched, seen, described. But nothing? To speak of it already makes it something. To imagine it means filling the void with an image. The idea seems to slip away as soon as you try to grasp it. If nothing is real, it must be unobservable. And if it is unobservable, how can it be known? That was the circle they often found themselves trapped in. Science, over centuries, tried to break that circle by redefining nothing in practical terms. A vacuum, for example, was once defined simply as a space without air. Pump out the atmosphere, and you have emptiness. That seems straightforward enough. But modern physics has complicated it again. Now we know that a vacuum without air is still full of fluctuating fields, virtual particles, forces, and energy. It is not nothing but a kind of something beneath things. And so the question returns, if what we thought was nothing turns out to be something, is there really any such thing as nothing at all? Some argue that nothing is an illusion, that it exists only in language. To speak of nothing is to mark the absence of a particular something, never a true void. The empty chair is empty only of a person, but it still contains air, light, radiation, fields. The empty jar is empty of liquid, but not of molecules bouncing inside. Even the emptiest vacuum, scrubbed of particles, cooled to near absolute zero, remains filled with fluctuations and energy. Perhaps there is no nothing. Perhaps the word is just a placeholder for a limit we cannot reach. Others take a subtler stance. They say that nothing is real, but it is not absolute. It is always relative to context. The nothing of one description becomes something of another. The vacuum of classical physics becomes a frothing field in quantum theory. The absence of matter becomes the presence of energy. In this view, nothing is a shifting horizon, a concept that evolves with knowledge. Each time we strip away what seemed fundamental, we find another layer beneath. There is also the perspective that nothing is creative. Without it, structure cannot exist. Consider music. A melody requires not only notes but pauses. Silence shapes sound, gives it rhythm and a meaning. Without silence, music would be noise, a blur without pattern. Or consider architecture. The walls of a building matter, but so do the spaces between them. A room is not the bricks that enclose it, but the emptiness in which people move and live. In this sense, nothing is not absence, but presence of a different kind, the background that allows form to emerge. Physics often finds itself echoing these ideas. The vacuum is not a void, but the stage upon which particles act. And yet, unlike music or architecture, this stage is not passive. It contributes actively, shaping the play. Particles gain mass through fields, forces arise from fluctuations, expansion is driven by energy of the vacuum. The background writes itself into the foreground. Nothing becomes everything. Still, the question lingers. Could there be a deeper nothing, a true absence beyond even fields and energy? Some physicists speculate about this when they discuss what may have existed before the Big Bang, or whether it is even meaningful to ask. If the universe arose from a quantum fluctuation, what was the vacuum that fluctuated? If inflation emerged from a false vacuum, what lay beyond? Perhaps we will never know. Perhaps nothing in its purest form is forever beyond science, not because it does not exist, but because it cannot be measured, cannot interact, cannot leave a trace. And yet, perhaps that is not troubling. After all, we live in the world of something, not in the world of pure nothing. Our minds are built to notice presence, difference, contrast. Nothing is useful to us as an idea, a foil, a way of describing what we are not seeing. It sharpens our sense of what is there. Without the concept of nothing, something would lose its meaning. Without absence, presence would not shine so brightly. It is curious to notice how often we use nothing in daily language, as if it were a familiar companion. "What are you thinking about?" someone asks. "Oh, nothing," comes the reply. Of course, the mind was not truly blank. It was drifting, unfocused, perhaps resting. Nothing here does not mean void, but rather something that defies easy articulation. Or when we say, there's nothing in the fridge, we do not mean the fridge contains a perfect vacuum. We mean nothing we want to eat. The word always conceals a relative meaning, never absolute emptiness. Even in meditation traditions, nothing has a role. In stillness, in letting thoughts go, practitioners sometimes speak of touching emptiness. Not as a barren void, but as a fullness, a clarity, a state where clutter falls away. It is a lived experience of nothing as fertile ground, the space in which awareness itself becomes vivid. Here again, nothing is not a dead end, but a beginning. For philosophers and physicists alike, the difficulty is that our words strain under the weight of these ideas. To call something nothing is paradoxical, since the very act of naming it gives it a presence in thought. That may be why the debate persists across centuries. Nothing is real, but only as a concept, never as a complete state. Every attempt to find it reveals more layers of something. The more closely you look, the less empty it seems. So is nothing real? Perhaps the best answer is that nothing as pure absence is not real in the physical universe, but nothing as a relative absence, as a fertile background, as a boundary to thought, is deeply real. It is real as a frame, as a contrast, as the silence that lets the music of existence play. Physics tells us that the vacuum is never empty. Philosophy reminds us that the very idea of emptiness shapes how we think. Together, they suggest that nothing and something are not opposites but partners, intertwined in every corner of reality. And as you let that idea settle, notice how it feels less like a puzzle to be solved and more like a gentle paradox to live with. Nothing may not exist as we once imagined, but it guides us, frames us, makes us aware of what is. Just as stars stand out against the black of night, the world shines against the background of nothing. When we speak of the vacuum inside your body or in the space between plates of metal, it feels local, manageable, something you can picture in a jar or in an atom. But when we widen our view to the whole universe, to billions of galaxies drifting through cosmic expansion, the vacuum becomes more than a curious detail. It becomes the dominant player in the fate of everything. Nothing, once dismissed as mere absence, turns out to be the quiet force shaping the story's ending. The universe is not static. We know this now with confidence. Galaxies are not fixed in their positions, nor is the cosmos balanced forever on some steady stage. Space itself stretches, and it stretches faster with time. The vacuum, through its energy, drives this expansion, and depending on how it behaves, the universe may face very different destinies. One possibility is the slow, eternal spreading, known as the Big Freeze. In this vision, dark energy, vacuum energy, remains constant, steadily pushing galaxies farther apart. Over billions of years, clusters separate until each becomes an island universe, no longer able to see the light of its neighbours. Stars will continue to burn, but fuel is finite. The brightest ones fade first, leaving dim red dwarfs and cooling embers. Eventually even those expire, and the cosmos grows darker. Black holes persist, swallowing the remnants, but even they are not eternal. Through Hawking radiation they evaporate, releasing their mass into faint trickles of energy. What remains is a vast, cold, thin sea, a universe emptied not by collapse, but by dispersal. In this ending, the vacuum wins by dilution. It stretches everything so far apart that structure itself fades. Another possibility is more dramatic, the Big Rip. If the energy of the vacuum is not constant but grows with time, expansion accelerates without limit. Galaxies are torn from clusters, stars from galaxies, planets from stars. The tearing does not stop at systems or bodies. Eventually, the expansion overcomes the forces that hold atoms together. Protons and neutrons themselves are ripped apart by the relentless stretching of space. In this ending, the vacuum wins by force, dissolving all bonds until there is nothing left but a scattering of particles spread across an ever-thinning field. There are gentler possibilities too. If dark energy weakens or reverses, gravity could eventually slow expansion. The universe might halt and begin contracting. This could lead to a big crunch, where galaxies rush back together, stars collide, black holes merge, and everything collapses into a final singularity. Or perhaps the contraction would bounce, leading to another cycle, a new expansion, another beginning. In such scenarios, the vacuum is not the destroyer, but the pendulum, swinging the cosmos between birth and death. Some theories imagine vacuum decay, a more subtle but equally startling fate. In this view, the vacuum we know is not the deepest possible state of reality, but a false vacuum, a local minimum of energy. Somewhere in the vastness, a fluctuation might trigger a bubble of true vacuum, a lower energy state. That bubble would expand at the speed of light, rewriting the laws of physics inside it. Particles would change, forces would shift, atoms might not even exist as we know them. The bubble would sweep through the universe without warning, erasing the familiar and replacing it with something alien. To outside observers, there would be no sensation, no time to prepare. The end would come instantly, silently, not through destruction, but through transformation. This idea may sound like a story for science fiction, but it emerges naturally from quantum field theory. If the vacuum is structured, with energy levels like hills and valleys, then what we call empty space might not be the absolute lowest valley. The possibility of a deeper valley, a more stable vacuum, means our universe might someday tunnel into it. Whether this will ever happen, or whether it is even possible within cosmic timescales, is unknown. But it is a reminder that even emptiness may have layers, and that what seems final may not be. Each of these scenarios, freeze, rip, crunch, decay, depends on how the vacuum behaves, and because we cannot yet measure its nature with precision, we cannot say which, if any, will unfold. What we can say is that the vacuum is not neutral. It is not the background against which endings happen. It is the cause, the script, the director of the final act. For us, as beings who live only a brief moment compared to cosmic times, these possibilities may feel abstract. After all, stars will shine for billions of years yet. The galaxies will not vanish from our skies tomorrow. The vacuum's ultimate decision plays out on scales far larger than our lives. But thinking about it brings perspective. The universe is not fixed. Its future is not static. The same nothingness that makes atoms possible and drives galaxies apart also holds the power to decide the very shape of eternity. It is humbling to realize that what we call nothing contains so much potential. The vacuum is not the absence of everything, but the presence of laws, fields, and energies that extend far beyond our imagination. It connects the smallest scales, fluctuations inside protons, to the larger scales, the fate of the cosmos. And in that connection, it reveals itself as the silent thread tying everything together. Imagine standing outside on a quiet night. The stars shimmer, distant and serene. To the eye, it feels timeless, as though they will always be there. But behind that serenity is motion, galaxies sliding apart, the vacuum's gentle hand guiding their drift. The sky you see is a momentary arrangement, a pattern that will not last forever. The constellations will stretch, the stars will fade, and in the far future even the galaxies will slip beyond sight. It is not a tragic ending, nor a dramatic one, but a quiet one, written by the same nothingness that fills the space between you and those stars. In that sense, the end of everything is not an alien intrusion. It is an extension of the same processes happening all around you, all the time. Atoms bound by emptiness, particles flickering in and out, forces emerging from fluctuations. The vacuum shapes your body, your world, your night sky. The future is simply the long unfolding of the same story. Nothing does not wait for the end. It has been here all along, shaping beginnings and middles as much as endings. As strange as it may sound, there is a kind of comfort in knowing that the end of everything is not a sudden interruption, but the natural continuation of the vacuum's quiet influence. The void does not intrude from outside, it grows from within as it always has. The end is simply another way of being written into the fabric of nothing. After travelling through ancient debates, through Newton's quiet stars, Einstein's fabric, the restless quantum fields, the Casimir plates, the flicker of virtual particles, and even the possibility of the universe dissolving into emptiness, we find ourselves here, pausing for a moment to simply take in what all of it means. The vacuum, the idea of nothingness, has carried us across scales from the body to the cosmos, from fleeting fluctuations to the end of everything. And now, as the night deepens and the mind grows slower, it is natural to let those ideas settle like dust after a long day, to rest in the quiet they leave behind. The vacuum is strange because it is both intimate and distant. It is in the atoms of your hand and in the gulf between galaxies. It is the reason you feel solid when you touch the ground, and the reason galaxies drift apart in the silence of space. It creates the illusion of nothing but hides layers of structure beneath. To think about it is to stand at the border between science and philosophy, where facts and measurements meet questions that do not resolve. And that border is not uncomfortable. It is a place where curiosity can rest, not because it has run out of answers, but because it sees how answers themselves open into more mystery. There is a certain peace in realizing that nothing is never truly empty. You may have felt at times that emptiness in life is something to fear, a gap, a hollow that swallows meaning. But the story of the vacuum tells a gentler truth. Emptiness is potential. It is the stage from which particles appear, the canvas upon which galaxies paint their spirals, the background that gives form to music, to words, to thoughts. When you find yourself staring into emptiness, whether in the night sky or in a quiet moment alone, remember that it is not absence. It is the hidden fullness from which everything emerges. Think of your body again, made mostly of space. It might sound unsettling, but it need not be. Instead, it is reassuring. You are proof that emptiness holds together. You are a structure of vacuum and fields, of atoms suspended across vast stretches of nothing. And yet from that fragile balance arises warmth, awareness, and life. If emptiness can give rise to you, then it is not barren. It is generous, providing the room in which existence unfolds. There is also comfort in knowing that the vacuum will outlast everything we know. Stars, galaxies, even black holes will fade, but the fields and fluctuations of the vacuum will persist. Nothingness, in this sense, is eternal. That may sound cold, but in the slow rhythm of thought, it can feel calming. Eternity is not noise or chaos. It is silence, steady and patient. To rest in that thought is to rest in the idea that behind all change, there is a stillness that continues. It is worth remembering too that the vacuum is not separate from you. It is not only the void between the stars, but the quiet inside every atom, the background hum in which every neuron of your brain fires. When you sit in silence, letting the world slow down, you're already in contact with it. The stillness you feel is not unlike the stillness of the cosmos. You're not apart from that silence, you are part of it. As you let these reflections move through you, notice how the mind begins to soften its grip on questions. The need to decide whether nothing is real, or whether the universe will end in a freeze or a rip fades into the background. What remains is the rhythm of thought itself, flowing across the emptiness of attention. In that way, the story of the vacuum becomes not just science, but a meditation. The paradox of nothing becomes a companion to rest with. Imagine again the night sky, a clear one, dark, away from city lights. The stars are faint, but enough to guide your gaze outward. Between each star is blackness, the void. To the eye, it looks empty, and yet you know now it is not. It is alive with fields, particles, and energy. The stars you see are like islands floating in an invisible ocean, and you standing here are floating in it too. The same vacuum stretches between the particles in your skin and the stars in the sky. It is one continuous thing, unbroken, seamless. When you breathe out, your breath joins it. When you breathe in, you draw it into your lungs. You're not separate from it. You are carried by it. This thought can be grounding as you let yourself settle into the quiet of the night. To feel yourself not as a small, isolated figure, but as part of the same emptiness that holds galaxies is to dissolve a little into the vastness, to rest in something larger than yourself. It is not a thought of isolation, but of belonging. The vacuum connects you to everything, even in its silence. And if the end of the universe one day comes, whether by freeze or rip or crunch or decay, it will not erase that connection. You are already of the vacuum, shaped by it, sustained by it. The end would only be another form of its unfolding. Nothing is not an intruder. It is your oldest companion. It was here before stars were born, and it will remain long after they fade. To think of that is not to invite fear, but to lean into a wider calm, a perspective that stretches far beyond the day-to-day. As the mind grows heavy with sleep, the vacuum offers a metaphor for rest. Just as emptiness gives rise to particles, to matter, to life, so does the stillness of rest give rise to renewal. Sleep is not absence, but preparation, the quiet that makes tomorrow possible. Lying here, listening, you're not vanishing into nothing. You're returning to the fertile silence that sustains you, and so, the vacuum, the nothing that is everything, becomes more than a topic of science. It becomes a reminder that silence is not a lack but a presence, that rest is not an interruption but a continuation. To embrace emptiness is not to lose yourself, but to find the space in which you belong. Thank you for being here, for listening, and for letting your mind drift through these quiet ideas tonight. If you found comfort in this slow journey through the science of nothing, you might consider subscribing or leaving a like, so you'll always have a place to return to when you need calm. For now, let the thought of the vacuum settle gently in you. Remember that the emptiness you've been hearing about is not absence, but a quiet fullness, a presence that connects you to the stars and to yourself. May your rest tonight be as vast and steady as the silence between galaxies, and may you wake with the same quiet strength that comes from knowing you are part of it all. Good night.